When you look up at the night sky, you don't just see stars. You see history written in light, stories traveling across unimaginable distances, whispers of creation itself. And behind that light, hidden in silence, lies one of the greatest mysteries of the universe. Black holes. They make no sound. They shine no light. Yet their presence can bend the very fabric of reality. Black holes are not just cosmic objects. They are riddles of existence, places where our current understanding of physics simply breaks down. Tonight, as you lie back, close your eyes, and prepare to rest, I invite you to join me on a long, gentle journey into their depths. This will not be a hurried trip. Time itself behaves strangely around black holes, stretching and twisting in ways that defy our everyday experience. In the same way, our exploration will move slowly, calmly, like drifting through the vastness of space. Think of this not as a lecture, but as an experience, a chance to wander through mystery and wonder, guided only by curiosity and imagination. Take a deep breath. Let your body relax. Picture yourself floating far above our world, beyond the blue oceans and white clouds, drifting past the edge of Earth's atmosphere. Out here, stars are no longer tiny pinpoints. They are radiant fires burning across a dark ocean. Some are being born, bright and young. Others are dying, collapsing in spectacular endings. And in those deaths, something extraordinary is sometimes left behind: a black hole. A black hole begins with a star, a giant, far more massive than our sun. After shining for millions or even billions of years, that star burns out. Its light fades, and in its final moment, it collapses under the weight of its own gravity. That collapse is so extreme that all the matter, all the energy, all the history of that star is crushed into a single point. From that point, not even light can escape. What remains is invisible, silent. A hole carved into the fabric of space-time itself, and yet, while invisible, a black hole is never truly hidden. Its gravity is so intense that it bends the path of light, distorts the space around it, and leaves a kind of glowing signature. Matter drawn to close spirals inward, heating up until it shines brighter than a million suns before vanishing beyond the event horizon. The point of no return. This is where our journey truly begins. Together, we will step closer and closer to this horizon, not in fear, but in curiosity. We will wonder, what lies inside? Is it nothing but darkness and destruction? Or could there be something more? A hidden bridge, perhaps, leading to another universe. But before we go deeper, let me prepare you for what's ahead. This is not just a scientific exploration. Yes, we will talk about the physics, about Einstein's theories, about the strange behavior of light and time. But we will also allow ourselves to imagine, to dream, to think of black holes not just as astrophysical objects, but as metaphors for the unknown. They are reminders that no matter how much we discover, there are still places where knowledge dissolves into mystery. So as you listen, let yourself relax. If you close your eyes, picture yourself slowly drifting toward a galaxy far away. Billions of stars stretch out before you, and hidden among them are black holes, silent guardians of secrets we cannot yet unlock. Feel how vast it all is, how infinite. In this infinity, you are safe, floating freely. Carried along by curiosity alone, you might even find your eyelids growing heavier as we continue. That's all right. This journey doesn't require full attention or effort. You can drift in and out of sleep as you please. The story of black holes will keep unfolding like the universe itself. Whether you are awake to hear every word or not, because in the end, black holes are not just about destruction. They are about possibility. Possibility that space and time are stranger than we can imagine. Possibility that within every collapse hides the seed of a new beginning. Possibility that what seems like an end may simply be a doorway to something else. So tonight, let us begin this journey together. Slow, steady, and infinite. A journey into the heart of darkness, where silence speaks louder than any sound. And where the boundaries of reality itself are tested. Black holes are waiting. Imagine drifting farther now, away from Earth, away from the Sun, past the outer planets, and beyond the frozen edge of our solar system. You are leaving behind the world you know, moving into the silent ocean of stars. Out here, scale becomes almost impossible to grasp. The nearest star beyond our Sun is more than 4 light-years away, which means that even traveling at the speed of light, it would take more than 4 years to reach it. And that is just our neighborhood. Beyond it lie billions of stars in the Milky Way, each surrounded by their own planets, each with their own stories. The Milky Way itself is only one galaxy among trillions scattered across the cosmos. It is in these galaxies, in their crowded centers, or in their quiet outskirts, that black holes are born. Every large galaxy we know of contains a giant black hole at its core. These are not the remnants of single stars, but supermassive black holes. Millions or even billions of times heavier than the Sun. Their gravity is so powerful that it shapes the orbits of entire systems of stars. In a way, black holes are not merely destroyers, they are architects. Without them, galaxies might not even hold together. It is a strange thought that something invisible, something that consumes everything that comes to close, can also be the anchor for creation. Black holes sit at the center of galaxies like silent hearts, pumping not blood, but gravity, giving structure to the spiral arms that stretch for hundreds of thousands of light years. As we float deeper into this thought, let us pause. The human mind struggles to imagine such numbers, such distances, such scales. Light years, billions of stars, trillions of galaxies, these are not things we can easily picture. We live on a planet where a long walk across a city already feels far. How then can we truly understand a galaxy? Or the idea of a black hole that outweighs millions of suns? Perhaps that is part of the mystery's power. Black holes remind us of the limits of perception. They are places where not only light is trapped, but also our imagination. We can describe them with equations, draw them in simulations, and detect their presence through the way they bend light and matter. Yet what lies inside remains hidden, unreachable. Still, even from a distance, black holes influence everything around them. Imagine a star wandering too close. Its light bends, its shape distorts, and then, in a brilliant flare of energy, the star is torn apart. Streams of matter spiral inward, glowing brighter and brighter until they disappear beyond the event horizon. For a brief moment, the invisible becomes visible. The black hole announces its existence not by shining, but by how it devours. And then there are the ripples in space-time itself. When black holes collide, they send out waves, gravitational waves that ripple through the universe like vibrations on the surface of a pond. Billions of years later, those ripples wash over Earth, and with sensitive instruments, we can detect them. Think about that for a moment. Somewhere in a distant corner of the universe, two black holes crashed together long before Earth even existed. And today, we can still hear their echo. This connection across time and space is what makes black holes so extraordinary. They are not just exotic objects hidden away in far-off galaxies. They are part of the story of the cosmos, a story we are still learning to read. Every observation we make, every signal we detect, is like a word in that story. As you listen, you may feel your thoughts drifting too. That is natural. In the face of such enormity, the mind tends to float. You don't have to hold on to every detail. Just let the vastness wash over you. Imagine yourself as small as a single grain of sand, carried on the winds of infinity, and yet still connected to the whole. Because you are, we are all part of this universe, woven from the same fabric of space and time. The atoms in your body were born in stars, scattered across space, and eventually gathered into you. And black holes, though mysterious and terrifying, are also part of that cycle. They are not outside of nature. They are nature taken to its most extreme. As we continue this journey, remember that black holes are not just objects to fear. They are reminders. Reminders of how much more there is beyond what we see. Reminders that our understanding is always incomplete, always waiting to be expanded. Reminders that mystery itself has value because it drives us to wonder. So, let us drift further still into that wonder. The galaxies pass us by, their spiral arms slowly turning, their cores glowing with unseen power. Somewhere ahead, waiting in the dark, is the event horizon, the place where light surrenders and time dissolves. We are not there yet. For now, we are only preparing ourselves, breathing in the scale of the cosmos, letting our minds expand to meet it. In this stillness, in this infinity. Black holes are waiting. Close your eyes for a moment and imagine standing at the edge of the known universe. Behind you lies everything familiar: the earth, the sun, the comfort of home. Before you, however, stretches a horizon of darkness and silence, endless and unbroken. Somewhere within that darkness are black holes, silent sentinels of mystery. What makes them so fascinating is not only what we know about them, but also what we don't. Science can describe how they form, how they warp gravity, and how they influence galaxies. But science, at least for now, cannot describe what happens once something crosses their boundary, the event horizon. It is there that knowledge stops and imagination begins. Think about this. The event horizon is not a solid surface. It is not a wall you could touch. It is, instead, a boundary in space where escape becomes impossible. Cross it, and every path forward bends inward. Deeper and deeper, toward the singularity, that single point of infinite density where space and time themselves collapse. What could exist beyond such a place? Is it an end? Or is it something else entirely? Some scientists wonder if black holes might be portals, not just to destruction, but to other universes. Could falling into one mean falling out somewhere else, in another reality altogether? It is speculation, yes, but it reminds us of something essential. Black holes push us to confront the limits of knowledge. They force us to ask questions that have no easy answers, and perhaps that is why they resonate so deeply. Because black holes are not just astrophysical phenomena. They are metaphors for mystery, for the unknown, for the places in life and in thought where our understanding dissolves. And all we can do is wonder. As you rest now, listening to these words, allow yourself to feel comfortable in that mystery. It is not something to fear. It is something to embrace. The unknown is part of existence. The unknown is part of being alive. Every discovery in human history began with not knowing, with curiosity, with the courage to ask. Imagine yourself drifting slowly toward a black hole. At first, it seems distant, a small sphere of darkness against a background of stars. But as you approach, space itself begins to change. Stars around it appear to stretch and bend, their light warped by the gravity of the unseen object. Time itself feels slower. The closer you move, the more reality feels altered. And then, at the horizon, you face a choice: to turn back toward the familiar, or to surrender to the unknown. For this journey, we will not turn back. We will step closer, not recklessly, but with quiet curiosity. Not with fear, but with calm. Because black holes, in all their mystery, are not just cosmic abysses. They are invitations, invitations to imagine what lies beyond the borders of certainty. So let yourself breathe deeply. Let yourself rest. If sleep comes, it is welcome. If your thoughts drift, they can drift freely. The universe does not hurry, and neither will we. Our journey will be long, slow, and full of wonder. Black holes have existed for billions of years. They can wait for us to catch up in this silence. As galaxies wheel slowly in the distance and stars are born and die, you are part of something immense. You are a witness to infinity. And tonight, you and I will walk together into that infinity. Guided by curiosity, sustained by wonder, and comforted by the knowledge that mystery itself is beautiful. When we look into the night sky, we are not just seeing pinpricks of light scattered across a dark canvas. We are, in truth, gazing into the very foundations of the universe itself. Stars are not simply decorations hung in the heavens. They are the engines of creation, the forges in which the elements of life are born, and the silent witnesses to the vast passage of cosmic time. To understand black holes, and indeed to understand the mysteries of space, we must first understand the story of stars. Every star begins as something almost unimaginably quiet and unassuming. A cloud of gas and dust, drifting in the cold vastness of interstellar space. These clouds, called nebulae, are cradles of creation. For millions of years, they may appear to float aimlessly, illuminated faintly by the light of nearby stars. Yet hidden within these clouds, an invisible drama is unfolding. Gravity, the most patient sculptor in the cosmos, slowly gathers atoms of hydrogen and helium, pulling them closer and closer together. At first, this process seems almost imperceptible. But over time, the cloud grows denser. The atoms collide more often, and the temperature begins to rise. Eventually, there comes a moment when the heart of the cloud ignites. Nuclear fusion is born, and with it, a star is lit. What was once darkness is now a beacon. Capable of burning for billions of years, stars are often thought of as eternal, but they too are bound by time. Their lives, though long compared to ours, follow a cycle that is both predictable and poetic. Small stars, like our sun, live calm and steady lives. They burn hydrogen slowly, shining gently for billions of years. Larger stars, however, live fast and die young. Their immense size demands enormous amounts of fuel. And so they blaze brightly, often in shades of blue and white, before collapsing in a spectacular death known as a supernova. It is in these supernovae that the universe becomes truly creative. The explosion scatters heavy elements carbon, oxygen, iron, and more into space. These are the building blocks of planets, of oceans, of air, and of life itself. When you breathe, when your heart beats, when you simply exist, you are living proof of the story written in the heart of a star. We are, quite literally, made of stardust. And yet, the story of stars is not just about creation. It is also about time itself. For when we look at them, we are not seeing them as they are now, but as they were long ago. Light takes time to travel, and the stars we admire in the night sky are often hundreds, thousands, or even millions of years away. To gaze at them is to look back into history, to witness moments that occurred long before human beings ever walked the earth. This dual role, both as creators of matter and markers of time, makes stars the true foundation of the universe. Without them, there would be no planets, no life, no history, and no future. They are, in every sense, the heartbeat of the cosmos. But stars do more than create and mark time. They also shape space itself. Their gravity sculpts galaxies. Their radiation influences the birth of new stars. And their deaths can trigger waves of creation across the universe. The life of a star is not isolated, is part of an endless cycle, one that connects the smallest atom to the grandest galaxy. In this way, the story of stars becomes the story of everything. They remind us that even the mightiest creations begin with something small and fragile, and that endings are not always the conclusion of a tale, but often the beginning of something new. As we prepare to explore time itself in the next part of this chapter, Let us pause for a moment to reflect. When you look at the stars tonight, remember that you are not just seeing light. You are seeing the memory of creation, the echoes of lives that began billions of years ago, and perhaps ended long before you were born. You are seeing time frozen in motion, delivered across the universe to your eyes. The foundations of the universe are written in starlight. And it is within this light that we find both our origins and our destiny. Asterisk. Time is perhaps the most mysterious companion of the universe. It is the quiet river that carries every star, every planet, and every living thing from birth to death. Yet, though it flows through us constantly, we rarely stop to think about what it truly is. We measure it with clocks, with calendars, with the rising and setting of the sun. But, in truth, time is far deeper than these human inventions. It is woven into the very fabric of reality. Imagine the universe as a grand tapestry. Space and time are not separate threads, but are woven together into something we call space-time. When we move through the universe, we are not just moving through space, we are also moving through time. Every moment you experience, every heartbeat, every memory, it's one step along that invisible path. For much of human history, time was thought to be absolute. People assumed it ticked the same way for everyone, everywhere, like a great cosmic clock. But in the early 20th century, Albert Einstein showed us that this picture was incomplete. Time, he revealed, is flexible. It bends, it stretches, and it can even slow down or speed up depending on how you move and where you are in the universe. This strange idea is known as relativity. Picture yourself standing still, watching a train speed by. For you, time feels normal. But for someone on the train, moving near the speed of light, time itself flows differently. Their seconds stretch compared to yours. To them, everything feels natural, but from your perspective, their clock ticks more slowly. This phenomenon, called time dilation, has been proven with precise experiments, even here on Earth. Gravity, too, affects time. The stronger the gravitational field, the slower time moves. Near something as massive as a star, or especially a black hole, time itself stretches out. For an observer far away, a clock near a black hole seems to slow. Its seconds stretching into minutes, its minutes into hours. This is not an illusion. It is the universe itself reshaping time. And so, stars are not only creators of matter, they are also keepers of time. Their light travels across the universe at a finite speed, and in doing so, it preserves a record of the past. When we look at the Andromeda Galaxy, for example, we are seeing it as it was more than 2 million years ago. Its present remains hidden, locked away until its light eventually arrives. To study the heavens is to study time itself, unfolding across distances so vast that they escape our everyday comprehension. This realization changes the way we see the cosmos. The universe is not a static painting. It is a living story, told moment by moment, with light carrying the chapters to us across the great gulf of space. We do not merely live in time, we are made of it, bound by it, and shaped by its currents. But what is time, really? Is it a river that flows from past to future? Or is it a landscape, with past, present, and future all existing at once, waiting for us to walk through? Physicists still debate this. Some argue that time is an illusion, a product of human perception. Others believe it is as real as the stars themselves. An essential ingredient in the cosmic recipe. For us, time is both familiar and unfathomable. It gives rhythm to our lives. It teaches us patience. It allows stories to have beginnings and endings. Yet, when viewed against the backdrop of the cosmos, our human sense of time becomes almost laughably small. A single second is the blink of an eye. A human lifetime is a spark. Stars live for billions of years. Galaxies dance together for trillions. And the universe itself. It has existed for nearly 14 billion years and may endure for countless billions more. Time also humbles us. It reminds us that change is inevitable, that nothing stays the same forever. Even the stars, as eternal as they seem, are temporary flames. And yet, within this impermanence lies beauty. Time gives meaning to moments. Without it, there could be no growth, no progress, no history. Time is not just a limit. It is the canvas upon which existence paints its story as we drift deeper into the mysteries of the cosmos. Remember this: every star you see is not just a point of light. It is also a time machine, showing you an image preserved across the ages. When you gaze at the night sky, you are not only looking outward, you are looking backward, into the deep corridors of cosmic history. And in this way, stars and time are forever entwined. One gives us the substance of the universe. The other gives us its rhythm. Together, they create the stage upon which all of existence unfolds. A black hole is not just an empty void. It is a region of space where matter, energy, and the very fabric of spacetime are pushed to their extremes. To understand a black hole, we must imagine a place where the ordinary rules of physics no longer apply. A place where gravity dominates utterly, and light itself can no longer escape. The first boundary of a black hole is called the event horizon. This is the invisible surface surrounding the singularity. Cross this boundary, and nothing returns. Not photons of light, not particles, not even information as we understand it. From the outside, the event horizon is a point of no return. To the distant observer, time seems to slow as an object approaches it. A star falling toward a black hole appears to freeze at the edge, glowing ever more brightly before fading from view. But for the object itself, time continues normally. Inside the event horizon lies the singularity, a point where density becomes infinite. Space and time collapse into one another, and the known laws of physics break down. No theory today can fully describe what occurs at the singularity. It is a place beyond our understanding, a realm where the mathematics of relativity and the quantum world collide. Some physicists speculate that new physics awaits discovery here, a unification of gravity, and quantum mechanics that could reveal secrets about the universe. Itself, the gravity near a black hole is so strong that it warps space-time. Imagine stretching a rubber sheet and placing a heavy ball in the center. The sheet curves around the ball, pulling smaller objects inward. Now imagine a ball so heavy, so dense, that the sheet tears into itself. That is a crude analogy for how spacetime behaves near a black hole. Light, which normally travels in straight lines, bends along these curves. Time slows. Distances stretch. Reality becomes a strange, distorted version of itself. Some black holes spin, dragging spacetime with them in a phenomenon called frame dragging. This rotation twists the paths of matter and light around the black hole, creating a swirling whirlpool of energy. Objects caught in this flow follow spiral paths, eventually joining the accretion disk, where friction and heat produce brilliant radiation. Even without crossing the event horizon, the influence of a black hole can be seen across light years of space. Black holes also play a role in shaping galaxies. Supermassive black holes at galactic centers regulate star formation by pulling in gas and matter, or by emitting jets of energy that push material outward. These jets, sometimes extending for thousands of light-years, can sculpt the shape of entire galaxies, influencing the cosmic landscape over unimaginable spans of time. One of the most fascinating aspects of black holes is their effect on time itself. Due to gravitational time dilation, time passes differently for someone near the event horizon compared to a distant observer. Near the black hole, seconds may feel like minutes, hours, or even years to an outside observer. This is not science fiction. It is a real consequence of Einstein's theory of general relativity. Approaching a black hole is, in a sense, a journey into the extremes of time. The interior of a black hole is a place where the known universe ends. What lies beyond the singularity, if anything, remains a matter of speculation. Some theorists propose that black holes may connect to other regions of space, or even other universes, through structures known as wormholes. A wormhole, sometimes called an Einstein-Rosen bridge, is a theoretical tunnel through space-time that links to distant points. While no wormhole has ever been observed, the mathematics of black holes allows for the possibility. Could a black hole be a gateway rather than a grave? We do not yet know. Black holes challenge our intuition at every turn. They bend light, slow time, and compress matter into points beyond comprehension. Yet, for all their strangeness, they are not anomalies. They are natural outcomes of gravity, mass, and the life cycles of stars. They are as much a part of the universe as planets, galaxies, and the void itself. Even though we cannot see inside a black hole, their presence is detectable. Astronomers observe the behavior of nearby stars, the light emitted by accretion disks, and the gravitational waves produced when black holes merge. These observations allow us to understand the invisible, to measure the unseeable, and to explore the edges of reality without ever crossing the threshold ourselves. And yet, for all the scientific understanding, black holes remain deeply mysterious. They are places of endings and perhaps of beginnings. They challenge the limits of knowledge, the boundaries of space and time, and the courage of the imagination. To study a black hole is to confront the unknown, and in that confrontation, we glimpse the profound beauty of the cosmos. As we prepare to move to Part 3, we will explore what would happen if someone entered a black hole, the theoretical consequences of falling past the event horizon, and the tantalizing possibility of black holes as gateways to other universes. Imagine, for a moment, drifting slowly toward a black hole. From a safe distance, it seems serene, a dark sphere, perfectly silent. Its presence revealed only by the stars bending around it and the light from its accretion disk. Yet as you approach, reality itself begins to shift. Space stretches, time slows. Gravity becomes an ever-tightening grip, pulling you inexorably toward the event horizon, the point of no return. If you were to cross that invisible boundary, what would happen? Science can offer theories, though none can fully describe the experience. The most famous is a phenomenon called spaghettification. As you fall toward the singularity, the difference in gravitational pull between your head and your feet, or any 2 points of your body, becomes extreme. You would be stretched lengthwise and compressed widthwise, elongated like a cosmic noodle. This is not metaphor. It is the direct consequence of gravity acting with unprecedented intensity. Inside the black hole, the familiar rules of physics dissolve. Time and space merge in ways we cannot intuit. Past, present, and future lose their ordinary meaning. From an outside observer's point of view, your fall appears to freeze at the event horizon, your image slowly fading into darkness. Yet for you, time flows normally, though every moment brings you closer to the singularity where known physics fails. Some physicists speculate that the singularity might not be a point, but a bridge. According to theories based on quantum gravity, the intense conditions inside a black hole could allow for connections to other regions of space-time, perhaps even other universes. This idea, while highly speculative, captures the imagination. Could a black hole be a doorway rather than a dead end? Could the ultimate act of falling into one be an act of cosmic travel? The concept of wormholes arises from similar thinking. If the singularity could somehow connect to another region of space, then a path through a black hole might emerge on the other side. Some theories suggest these bridges could be stable under certain exotic conditions. though no observational evidence has yet confirmed such a phenomenon. Still, the mathematics of general relativity allows for it, a tantalizing hint that the universe may be far stranger than we have ever imagined, even if no other universe awaits. The journey into a black hole is extraordinary in its consequences. Matter, once inside, contributes to the growth of the black hole. Energy, angular momentum, and mass are absorbed, increasing its size and strength. Supermassive black holes, feeding over billions of years, can grow to unimaginable proportions, anchoring entire galaxies and influencing the cosmic landscape in ways that are both violent and majestic. Black holes also challenge our understanding of information. According to classical physics, information about matter falling into a black hole is lost forever. Yet quantum mechanics suggests that information cannot truly be destroyed. This paradox, the information paradox, has sparked decades of debate, with ideas ranging from information being encoded on the event horizon to it being preserved in another universe. In this way, black holes are not only cosmic objects, they are puzzles questioning the fundamental nature of reality itself. Despite their danger, black holes are not malevolent. They are not hunters lying in wait. They are natural phenomena following the laws of the universe with a quiet inevitability. They remind us of the limits of control and the humbling vastness of space. Observing them safely from light years away allows us to study extremes of matter, energy, and time conditions impossible to replicate on Earth. There is a poetic lesson in black holes. They are places of both destruction and creation. The death of a star can birth a black hole, and that black hole can shape galaxies, trigger new star formation, and influence cosmic evolution. Even as matter disappears beyond the event horizon, the effects ripple outward, leaving an imprint on the universe. They are a testament to the interconnectedness of all things, a reminder that endings can lead to beginnings, and that the invisible can shape the visible. And so, as we drift farther in this contemplation, black holes become more than astrophysical objects. They are symbols of the unknown, the infinite, and the limits of understanding. They challenge imagination, beckon curiosity, and remind us that the universe contains realms where human perception and science must stretch to keep pace. To understand a black hole, we must explore its anatomy. Though invisible in the traditional sense, a black hole has distinct regions, each with unique properties. By examining these regions, we can begin to picture the remarkable structure of these cosmic objects, even if they remain forever beyond our physical reach. At the very center lies the singularity, the ultimate core of the black hole. Here, matter is compressed into an infinitely small point, and density becomes unimaginable. The singularity is where gravity reigns supreme, so intense that it overwhelms all other forces. Space and time collapse upon themselves, creating a region where the laws of physics as we know them no longer apply. It is a realm of extremes, a point of both mystery and fascination. Surrounding the singularity is the event horizon, often referred to as the point of no return. This is not a physical surface, but a boundary in space-time. Once any matter or light crosses the event horizon, escape is impossible. To an external observer, objects appear to slow as they approach this boundary, stretching out in time and fading from view. Yet for the object itself, time seems to flow normally, an eerie difference in perception dictated by the intense curvature of space-time. Beyond the event horizon lies the ergosphere in rotating black holes, also known as Kerr black holes. Unlike the static event horizon, the ergosphere is a region where space-time is dragged along by the black hole's rotation. This phenomenon, called frame dragging, can twist matter and energy, creating spiraling trajectories and powerful jets of radiation. Within the ergosphere, energy can actually be extracted, a process theorized to power some of the most energetic phenomena in the universe. The space surrounding a black hole is rarely empty. Most black holes are surrounded by an accretion disk, a swirling ring of gas, dust, and stellar debris spiraling inward. Friction within the disk heats this matter to extreme temperatures, causing it to emit X-rays and gamma rays. These energetic emissions are often the only visible signs of a black hole, revealing its presence and influence across vast distances. The accretion disk also provides insight into the black hole's behavior, including its spin, mass, and the dynamics of matter at the edge of the event horizon. Magnetic fields also play a crucial role in shaping the anatomy of a black hole. Twisted and intensified by the rotation of the disk, these fields can channel matter into relativistic jets, streams of particles ejected at near-light speeds. These jets can extend for thousands of light-years, influencing the formation of stars and galaxies far from the black hole itself. In this way, a black hole's influence extends far beyond its invisible boundaries, reaching across the cosmic landscape. Another intriguing feature of black holes is gravitational lensing, a direct consequence of their intense gravity. The curvature of space-time bends the path of light passing near the black hole, creating distorted, magnified, or even multiple images of background stars and galaxies. In essence, a black hole acts like a natural telescope, warping the view of the universe itself. This effect not only allows astronomers to detect black holes indirectly, but also serves as a reminder of the profound warping of reality near these extreme objects. Black holes come in different types, each with its own anatomy and characteristics. Stellar black holes form from the collapse of massive stars, typically ranging from a few to tens of solar masses. Intermediate mass black holes are heavier, possibly formed by the merging of smaller black holes or dense star clusters. Supermassive black holes, millions to billions of times the Sun's mass, anchor the centers of galaxies, including our own Milky Way, though vastly different in scale. All black holes share the same fundamental structure: singularity, event horizon, and often accretion disk and jets. The temperature of a black hole is also an intriguing feature. According to quantum theory, black holes are not completely black. Stephen Hawking proposed that they emit faint radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon and implies that black holes can slowly lose mass over astronomical timescales. In theory, a black hole could eventually evaporate completely, though the process would take far longer than the current age of the universe for most black holes. Understanding the anatomy of a black hole challenges our perception of space, time, and matter. Each region, from the singularity to the ergosphere, from the accretion disk to the relativistic jets, reveals a different facet of extreme physics. Black holes are laboratories of the cosmos, where matter is stretched, time is distorted, and energy is unleashed on scales that defy human imagination. Yet, for all their complexity, black holes are governed by remarkably simple principles. Despite the chaos and violence around them, they are defined by just a few characteristics: mass, spin, and electric charge. These parameters determine everything about their behavior, from the shape of the event horizon to the dynamics of the accretion disk. In a sense, black holes are simple, yet unfathomably deep. The perfect paradox of the universe. In the next part, we'll explore how black holes interact with their surroundings, including the capture of matter, the production of cosmic jets, and the ways they influence entire galaxies. We will also delve into the role of black holes in the cosmic ecosystem, showing how these mysterious objects are both destructive and creative forces in the universe. Black holes are not isolated objects. They exist within a dynamic cosmic environment. Though invisible in themselves, their gravitational pull and energetic emissions shape the universe around them. From the capture of gas and dust to the regulation of star formation, black holes are both destroyers and creators, playing a pivotal role in the cosmic ecosystem. One of the most striking ways black holes influence their surroundings is through accretion. As matter falls toward a black hole, it forms a swirling accretion disk. Friction within this disk heats the matter to incredible temperatures, producing X-rays and gamma rays that can be detected across vast cosmic distances. This process converts gravitational energy into radiation with astonishing efficiency, far more than nuclear fusion in ordinary stars. In this sense, black holes are not only sinks of matter, but also immense engines of energy, illuminating the cosmos in the process. Some black holes, particularly supermassive black holes, produce relativistic jets, streams of particles expelled at nearly the speed of light. These jets are guided by magnetic fields and can stretch for thousands of light years, far beyond the black hole itself. The energy carried by these jets can disrupt nearby star-forming regions or trigger the formation of new stars by compressing gas clouds. In this way, black holes act as cosmic sculptors, shaping galaxies and influencing the evolution of the universe on the largest scales. The gravitational influence of black holes extends beyond the immediate vicinity of the event horizon. Their immense pull can warp space-time, bending the paths of stars, gas clouds, and even light itself. This warping, known as gravitational lensing, allows astronomers to observe distant galaxies and detect otherwise invisible objects. By studying these effects, scientists can measure the mass and spin of black holes, map the distribution of matter in the universe, and even probe the mysterious nature of dark matter and dark energy. Black holes also act as cosmic recyclers. When a star ventures too close and is torn apart by tidal forces, its material is either swallowed by the black hole or flung back into space. This process enriches the surrounding interstellar medium with heavy elements, contributing to the formation of new stars, planets, and ultimately life. Even in destruction, black holes participate in the ongoing cycle of cosmic creation at the centers of galaxies. Supermassive black holes anchor massive structures, controlling the motion of stars and gas clouds. The Milky Way, for instance, contains a supermassive black hole called Sagittarius A** at its heart, weighing about 4 million times the mass of the Sun, though relatively quiet now. It has likely shaped the evolution of our galaxy over billions of years. Observations of more active galactic nuclei reveal black holes consuming vast amounts of material, producing bright quasars visible across the universe. Interestingly, black holes can also merge, creating even larger black holes and releasing immense amounts of energy in the form of gravitational waves. These ripples in spacetime, predicted by Einstein and detected for the first time in 2015, provide a new window into the universe. Each merger carries information about the masses, spins, and histories of the colliding black holes, offering insights into the evolution of stars, galaxies, and cosmic structure. The influence of black holes is not only physical, but also temporal. Time behaves differently near a black hole due to gravitational time dilation. Clocks close to a black hole tick more slowly than those farther away. For an observer hovering near the event horizon, seconds may stretch into minutes, hours, or even years relative to a distant observer. This effect has profound implications for understanding relativity, causality, and the ultimate limits of experience in extreme environments. Moreover, black holes may have implications for the fundamental nature of reality. The information paradox, for instance, challenges the principle that information cannot be destroyed. If matter and information fall into a black hole, what happens to them? Are they lost forever or somehow preserved? Theoretical physicists propose that information may be encoded on the event horizon or even transferred to other universes. Black holes, therefore, are not only astrophysical objects, but also laboratories for the deepest questions in physics. Despite their destructive reputation, black holes are essential components of the cosmos. They regulate galactic evolution, recycle matter, power some of the most energetic phenomena, and test the boundaries of physical law. In essence, black holes are both guardians and architects of the universe, shaping reality in ways that are subtle, profound, and often invisible to the naked eye. In the next part, we will explore the most mysterious aspects of black holes, including Hawking, radiation, quantum effects, and the tantalizing possibility that black holes could serve as portals to other universes. We will examine how these extreme objects challenge our understanding of physics and hint at a reality far stranger than everyday experience. While classical physics explains much about black holes, their formation, structure, and gravitational influence, quantum mechanics introduces a whole new level of mystery. At the intersection of general relativity and quantum theory, black holes reveal phenomena that challenge our deepest understanding of the universe. One of the most fascinating predictions is Hawking radiation, proposed by Stephen Hawking in the 1970s. According to quantum mechanics, even empty space is not truly empty. It teems with temporary particle-and-particle pairs that appear and vanish spontaneously. Near the event horizon, one particle may fall into the black hole while the other escapes, producing a faint emission of radiation. This process implies that black holes are not entirely black. They slowly emit energy and can, in theory, evaporate over incomprehensibly long time scales. Hawking radiation also introduces the information paradox. If a black hole evaporates completely, what happens to the information about the matter it consumed? Classical physics suggests that information is lost, violating quantum principles that assert information cannot be destroyed. Resolving this paradox is one of the greatest challenges in modern theoretical physics, prompting hypotheses such as information being stored on the event horizon in a holographic form or escaping to other universes. Beyond Hawking radiation, black holes provide a testing ground for quantum gravity, the elusive theory that unites general relativity and quantum mechanics. The singularity at the center represents a point of infinite density, where space-time curves infinitely and classical physics fails. Quantum effects are expected to dominate here, potentially smoothing out the singularity or replacing it with a bridge to another region of space-time, a concept sometimes referred to as a Planck star, though purely theoretical. These ideas push the limits of human imagination and scientific creativity. The notion of wormholes arises naturally from these extreme conditions. If the singularity could connect to another part of space-time, a black hole might not be an endpoint, but a gateway. Wormholes or Einstein-Rosen bridges are predicted by general relativity, though they would require exotic matter to remain stable. While no observational evidence confirms their existence, they remain a tantalizing possibility. In speculative physics, a black hole could act as a portal to distant regions of our universe or even entirely different universes. Some theories, even, suggest parallel universes may exist behind black holes. If the singularity leads to a new region of space-time, then falling into a black hole could, in theory, transport matter to a completely different reality. These ideas border on the philosophical as much as the scientific, inviting questions about existence, observation, and the nature of reality itself. What does it mean for something to exist if it has passed beyond an event horizon? Could consciousness survive such an extreme journey, or would it dissolve into the fabric of space-time? Black holes also play a central role in the study of cosmic censorship. Physicists propose that singularities are always hidden within event horizons, protecting the rest of the universe from their extreme effects. This cosmic censorship conjecture implies that while singularities are regions of infinite curvature, their influence on the observable universe is constrained. Yet theoretical exceptions, like naked singularities, remain a subject of debate, pushing scientists to explore the limits of general relativity. On a more practical level, black holes offer a window into the early universe. by studying the distribution, mass, and spin of black holes. Astronomers can infer details about star formation, galaxy evolution, and the distribution of matter shortly after the Big Bang. Black holes are, in a sense, cosmic archaeologists, preserving the history of the universe in their gravitational footprints. Despite the extreme physics, black holes are also objects of beauty and elegance. Their simplicity defined primarily by mass, spin, and electric charge contrasts with the complexity of their interactions and surroundings. They are cosmic paradoxes, simple yet complex, destructive yet creative, invisible yet influential. They stretch our imagination, forcing us to consider realms where the ordinary rules of space and time no longer apply. Ultimately, the study of black holes sits at the frontier of human knowledge. They challenge our understanding of space, time, matter, and information. They invite speculation about the possibilities of other universes, hidden dimensions, and cosmic journeys beyond the event horizon. For those who observe from afar, black holes are both frightening and mesmerizing. They are laboratories of the extreme windows into the fundamental workings of reality, and symbols of the infinite mysteries that surround us. As we conclude this chapter, we recognize that black holes are not merely objects to be studied. They are profound teachers. They remind us of the limits of understanding, the power of imagination, and the beauty of the universe's most extreme phenomena. In the next chapter, we will examine the hypothetical consequences of entering a black hole, exploring both the terrifying and wondrous possibilities of venturing beyond the point of no return. The event horizon marks the boundary between the known and the unknowable. It is the threshold where space-time twists and bends, where light itself can no longer escape. Crossing it is a journey that challenges both the imagination and the laws of physics. For a distant observer, an object approaching the event horizon appears to slow, frozen in time, fading as it approaches the ultimate point of no return. But for the traveler, time flows normally, each moment bringing them deeper into a realm beyond comprehension. Imagine drifting toward a black hole, feeling the pull of gravity increase exponentially. This is not a gentle descent. It is an inexorable attraction toward a point of infinite density. The closer you get, the more space-time stretches and compresses, creating extreme tidal forces. The difference in gravitational pull between your head and feet becomes so great that your body would be elongated into a thin, elongated shape, a process known as spaghettification. This is the direct manifestation of gravity at its most extreme, a force capable of reshaping matter itself. Yet crossing the event horizon is not immediately violent. In some scenarios, particularly with supermassive black holes, the tidal forces at the horizon may be surprisingly gentle. You could, theoretically, pass this boundary without feeling immediate destruction. The true extremes, the ultimate distortion of matter and time, occur as you approach the singularity at the black hole's core. Inside the event horizon, the normal rules of space and time no longer apply. Directions become uncertain, and the concepts of here and there lose their usual meaning. The singularity lies ahead, inevitable and absolute, a destination dictated by the curvature of space-time itself. In this region, physics as we know it breaks down, and our classical understanding of reality becomes irrelevant. Every particle, every wave, every strand of energy is drawn toward the singularity, contributing to its ever-growing density. One of the most profound mysteries of crossing the event horizon is the fate of information. According to classical physics, all details about the matter falling in are lost to the outside universe. Quantum mechanics, however, forbids the destruction of information. This leads to the black hole information paradox, a puzzle that continues to challenge theoretical physicists. Some propose that information is encoded on the event horizon in a holographic form, a radical concept suggesting that the entire three-dimensional interior of a black hole may be projected onto its four-dimensional boundary. Beyond the purely theoretical, black holes also inspire speculation about the possibility of portals to other regions of space. Wormholes or Einstein-Rosen bridges are hypothetical connections linking a black hole to another part of space-time. If such structures exist, the singularity might not signify an end, but a gateway. Matter entering a black hole could emerge in another universe, in a distant galaxy, or in a different dimension altogether. While this remains speculative, it tantalizes the imagination, raising questions about travel, survival, and the true nature of reality. The concept of parallel universes emerges naturally from these ideas. Some models of cosmology suggest that black holes could create or connect to alternate realities, each with its own distinct laws of physics. In such a scenario, falling into a black hole might not result in annihilation, but in transference and ultimate journey to another cosmic realm. Philosophically, this challenges our understanding of life, existence, and consciousness. Could awareness persist through such an extreme transition, or is it inevitably absorbed into the fabric of space-time? Even for observers who do not venture inside, black holes influence the universe in profound ways. Gravitational waves, produced when black holes collide, ripple through space-time, carrying information about their mass, spin, and history. These waves have been detected by instruments like LIGO, opening a new window into the cosmos. Black holes are no longer just theoretical curiosities. They are observable actors, shaping the universe in measurable, tangible ways. Within the event horizon, space-time is warped to extremes. Time flows differently, distances distort, and the familiar relationship between cause and effect becomes ambiguous. In some models, approaching the singularity could allow glimpses of the entire history of the universe, a perspective where past, present, and future coexist in a single, incomprehensible moment. This is not just science fiction. It is a direct consequence of Einstein's equations under conditions of extreme gravity. As you journey further inward, the singularity looms ever closer. The final moments before reaching it are a fusion of gravitational extremes, tidal forces, and warped time. Matter, energy, and information converge into a single point, a nexus of cosmic mystery. Beyond this, our current understanding ceases. What lies beyond is a realm of speculation, a frontier where physics, philosophy, and imagination intersect. Crossing the event horizon is therefore both terrifying and awe-inspiring. It represents the ultimate boundary of human knowledge and experience. The black hole is not merely an object. It is a threshold, a symbol of the limits of perception, and a gateway to questions that may never be fully answered. In the next part, we will explore what might exist inside a black hole, including speculative concepts such as alternate universes, wormholes, and the theoretical experience of an explorer venturing beyond the singularity. We will delve deeper into the mysteries of space-time, matter, and consciousness at the edge of the known universe. Black holes are among the most enigmatic objects in the cosmos. Their immense gravitational pull, the warping of space-time around them, and the strange phenomena occurring at their event horizons all contribute to their mysterious power. They are not just voids in space. They are engines of the universe, influencing everything from star formation to the evolution of entire galaxies. The first layer of this hidden power comes from gravity, the fundamental force that defines a black hole. When a massive star collapses at the end of its life, gravity overwhelms all other forces, compressing matter into a singularity. This point contains all the mass of the original star within an infinitely small space, creating a gravitational field so strong that nothing, not even light, can escape. Gravity becomes a controlling force, not just locally, but on a cosmic scale, shaping the orbits of stars, the motion of gas clouds, and the formation of galaxies. Surrounding the singularity is the event horizon, the invisible boundary that marks the point of no return. Crossing this threshold means venturing into a region where the normal rules of physics break down. Tidal forces stretch matter to extreme proportions, and time itself behaves differently. From the perspective of an outside observer, objects approaching the event horizon seem to slow and fade, yet for the object itself, time continues, normally a surreal experience that defies ordinary intuition. Black holes also wield their power through rotation. Many black holes spin, and this rotation drags space-time around with it, a phenomenon known as frame dragging. This effect can twist matter and energy, producing spiraling accretion disks and powerful relativistic jets. The spinning black hole, in effect, becomes a cosmic dynamo, converting rotational energy into matter and radiation ejected across thousands of light-years. These jets can impact star formation, disrupt nearby gas clouds, and influence the evolution of entire galaxies. Another fascinating aspect of black hole power is the ability to bend light through gravitational lensing. The intense curvature of space-time around a black hole warps the path of light, magnifying and distorting the appearance of background stars and galaxies. This not only allows astronomers to detect black holes indirectly, but also demonstrates the immense influence a black hole exerts on its surroundings. Light, the fastest thing in the universe, cannot escape the grip of a black hole without being dramatically altered. Black holes also produce Hawking radiation, a subtle but profound demonstration of their mysterious power. At the quantum level, particle and antiparticle pairs spontaneously appear near the event horizon. Occasionally, one particle escapes while the other falls in, creating a faint emission of energy. This radiation implies that black holes are not eternal. They slowly lose mass over unimaginable timescales. Hawking radiation bridges the macroscopic world of gravity with the microscopic realm of quantum mechanics, revealing black holes as laboratories for the most fundamental laws of physics. In addition to these forces, black holes play a critical role in galactic ecosystems. By regulating the motion of stars, the flow of gas, and the dynamics of matter, they shape the structure and evolution of galaxies. Supermassive black holes at galactic centers anchor vast star systems, and their influence extends far beyond the visible regions of galaxies. Even distant matter can be subtly affected, a testament to the far-reaching power of these cosmic phenomena. The mysterious power of black holes is also evident in their ability to merge and create gravitational waves. When two black holes collide, they release ripples in space-time that travel across the universe. These gravitational waves, detected by observatories like LIGO, offer a direct glimpse into the extreme interactions of massive objects. Each wave carries information about the masses, spins, and energies involved, allowing scientists to study black holes in unprecedented detail. Finally, black holes are objects of profound theoretical significance. They challenge our understanding of information, time, and reality. The information paradox, the possibility of wormholes, and the potential connection to other universes all suggest that black holes are more than simple cosmic vacuums. They are points where the laws of physics are pushed to their limits, where our understanding of space and time must be reconsidered, and where imagination and science converge. In the next part, we will explore the potential of black holes as gateways to other universes, the speculative physics of wormholes, and the philosophical questions that arise when considering these cosmic powerhouses. We will examine how the mysterious forces of black holes might open doors to realms far beyond our current understanding. Black holes, for all their destructive reputation, might also hold the key to the universe's most extraordinary possibilities, gateways to other regions of space, or even entirely different universes. While these ideas remain speculative, Theoretical physics offers intriguing hints that the singularity at a black hole's core may not signify the absolute end of matter and information. Instead, it could be a threshold, a bridge between known reality and realms beyond comprehension. The concept of a wormhole, or Einstein-Rosen bridge, arises naturally from the mathematics of general relativity. A wormhole is essentially a tunnel through spacetime connecting to distant points in the universe. In theory, a black hole could serve as one end of such a tunnel, with the other end emerging in another galaxy, another era, or even a parallel universe. This possibility, though unproven, fuels both scientific inquiry and the imagination, inspiring visions of cosmic travel that surpass the limits of conventional space exploration. For matter falling into a black hole, the experience is extreme. Approaching the singularity, gravitational forces stretch and compress all objects, distorting space and time. Yet if a wormhole exists, these forces might be navigable, allowing matter or energy to emerge elsewhere. Such a process would challenge our understanding of physics at the deepest level, potentially reconciling general relativity with quantum mechanics. Here, the extreme environment of a black hole becomes a laboratory for the universe's most profound mysteries. Speculation about parallel universes also arises from black hole physics. If each singularity represents a point of infinite density and warped spacetime, it may connect to a new, separate cosmos. Some theoretical models suggest that when matter collapses into a black hole, could trigger the formation of a baby universe, a separate spacetime bubble expanding independently of our own. In this view, black holes are not just endpoints. They are creators, giving rise to new realities hidden from our observation. Quantum mechanics adds an additional layer of intrigue. The holographic principle proposes that all information contained within a volume of space can be represented on its boundary. For black holes, this means that everything falling in is encoded on the event horizon, possibly preserving information even if the singularity is unreachable. This raises profound questions. Could this encoding be a form of communication with other universes? Could the universe itself be a holographic projection emerging from black hole boundaries? Such ideas, though speculative, highlight the astonishing potential of black holes to challenge our understanding of reality. Black holes as cosmic gateways are not limited to hypothetical travel. Their influence on spacetime allows for the creation of extreme gravitational gradients, which could warp trajectories and create shortcuts through space. In theory, an advanced civilization might harness such gradients to travel vast distances almost instantaneously, using the natural power of black holes to bridge otherwise impossible gaps. While purely speculative today, such concepts underscore the incredible energy and potential locked within these mysterious objects. Moreover, black holes may reveal insights into the birth and evolution of the universe itself. If black holes can generate new universes or connect to alternate realities, they may play a role in the cosmic cycle of creation and destruction. Each black hole could serve as a seed for new spacetime, a conduit through which matter and energy propagate into previously inaccessible dimensions. In this sense, black holes are not mere voids, they are engines of cosmic renewal, hidden architects of a multiverse that extends far beyond our observational reach. The philosophical implications are equally profound. If black holes are gateways, then the concept of an end becomes relative. Death, destruction, and absorption might be reinterpreted as transformation, transference, or passage into another realm. Consciousness, matter, and information could continue in ways we cannot perceive, offering a radical reimagining of existence itself. In contemplating black holes, we confront questions that blend science, philosophy, and even spirituality. Observational evidence, though indirect, hints at the extraordinary effects of black holes. Relativistic jets, gravitational waves, and the motions of nearby stars all reflect the immense power and influence of these cosmic objects. Yet the possibility of hidden pathways through spacetime remains largely theoretical, awaiting confirmation from future discoveries, advanced simulations, and perhaps new physics beyond our current models. In essence, black holes occupy a dual role. They are both destroyers and potential creators. They consume matter, warp time, and distort space. Yet they may also harbor the conditions for phenomena that extend beyond our universe. By studying them, we probe not only the limits of physics, but the possibilities of existence itself. Black holes, in their mysterious power, invite us to imagine worlds beyond the observable, realms where the familiar rules of reality may no longer apply. In the next part, we will examine the ultimate mysteries of black holes, including quantum effects, Hawking radiation, and the speculative idea of using black holes as portals for exploration. We will explore what might lie beyond the event horizon and how these extreme cosmic forces continue to challenge human understanding. Black holes are not merely cosmic vacuum cleaners. They are also the universe's most profound laboratories, where quantum mechanics and general relativity collide. The ultimate mysteries of black holes lie at the intersection of these two foundational theories, revealing phenomena that challenge our understanding of time, space, and the very fabric of reality. One of the most intriguing aspects is Hawking radiation, a quantum process that allows black holes to emit particles and slowly lose mass, unlike the massive gravitational effects that dominate classical black hole behavior. Hawking radiation emerges from quantum fluctuations near the event horizon. Virtual particle-on-type-particle pairs constantly form and annihilate in empty space. Occasionally, one particle falls into the black hole while the other escapes, producing a faint glow that can, over unimaginable timescales, cause the black hole to evaporate entirely. This subtle radiation provides a bridge between the macroscopic and microscopic worlds, highlighting the interplay of gravity and quantum physics. Hawking radiation also raises the information paradox, one of modern physics' most tantalizing puzzles. If a black hole eventually evaporates, what happens to the information contained in the matter it consumed? Quantum theory dictates that information cannot be destroyed, yet classical physics suggests otherwise. Resolving this paradox has led to radical ideas, such as the holographic principle, which proposes that all the information swallowed by a black hole is encoded on its event horizon. This principle suggests that the universe itself may be a holographic projection, where three-dimensional reality emerges from information encoded on two-dimensional boundaries. Another frontier involves the singularity at the center of a black hole. Classical physics predicts an infinitely dense point where curvature of spacetime becomes infinite. Yet quantum mechanics hints that this singularity might be replaced by a more complex structure. Some theories propose Planck stars or other exotic objects that could resolve the singularity, preserving information and allowing the laws of physics to remain consistent even in these extreme conditions. Understanding this structure could unify quantum mechanics with general relativity, revealing a deeper truth about the cosmos. The concept of wormholes or Einstein-Rosen bridges also emerges from these extreme conditions. While highly speculative, a black hole might act as one end of a tunnel connecting distant points in spacetime. If stable wormholes exist, matter and energy could theoretically traverse them, offering shortcuts across galaxies or even between universes. The notion of using black holes as portals, though far beyond our current technological capabilities, captivates both scientists and dreamers, hinting at possibilities that extend the boundaries of exploration and imagination. Some physicists even speculate that black holes could harbor entirely new universes within their singularities. These baby universes, connected through extreme space-time curvatures, might operate under their own physical laws, expanding independently from our observable universe. In this scenario, black holes are not simply endpoints, but seeds of creation, generating new realms beyond the reach of observation. The idea stretches our understanding of reality, prompting questions about the nature of existence, consciousness, and the ultimate fate of matter that crosses the event horizon. Quantum entanglement adds another layer of mystery. Particles near a black hole's event horizon may become entangled with distant particles, creating connections across vast distances. This phenomenon challenges our notions of locality and causality, suggesting that black holes could influence regions far beyond their immediate gravitational pull. Entanglement at such extreme scales remains largely theoretical. Yet it underscores the mind-bending possibilities inherent in these cosmic giants. Time itself behaves differently in the vicinity of a black hole. Gravitational time dilation slows the passage of time for objects near the event horizon relative to distant observers. For a hypothetical traveler, seconds might stretch into years, revealing a reality where the flow of time is no longer absolute. This extreme warping challenges our intuitive understanding and provides profound insights into the nature of space-time itself. Finally, black holes serve as a reminder of the universe's vast unknown. They test the limits of human understanding, revealing both the power and the humility inherent in scientific exploration. From the destruction of stars to the potential creation of new universes, from Hawking radiation to quantum entanglement, black holes remain at the frontier of discovery. They are objects of awe, fear, and inspiration, cosmic portals to questions that may never be fully answered. In conclusion, the ultimate mysteries of black holes lie not only in their physical properties, but in the questions they pose about reality itself. They challenge our notions of space, time, information, and existence. As scientists continue to probe these enigmatic objects, each discovery opens new doors to understanding, revealing a universe far stranger, more complex, and more beautiful than ever imagined. Black holes are not just astronomical phenomena. They are the universe's most profound teachers, inviting us to explore the unknown, to confront the limits of comprehension, and to imagine the infinite possibilities that lie beyond the visible cosmos. Crossing the event horizon of a black hole is unlike anything in ordinary experience. This invisible boundary represents the ultimate threshold in the universe, a point beyond which escape becomes impossible, even for light. To imagine venturing past it is to confront extremes of space, time, and gravity that defy human intuition. For those observing from afar, objects nearing the event horizon appear to freeze in time, fading gradually as gravitational redshift stretches their light. Yet for the traveler themselves, time flows normally, each moment an inexorable march deeper into the unknown. As one descends, the tidal forces become increasingly significant. These forces arise because the black hole's gravity acts differently on different parts of an object or body. Near the singularity, the gravitational pull on one end of an object may vastly exceed that on the other, stretching it into a long, thin shape, a process known as spaghettification. The phenomenon is more extreme in smaller black holes, where the singularity is closer to the event horizon. In supermassive black holes, however, the tidal gradient at the horizon may be surprisingly gentle, allowing passage across the boundary without immediate destruction. Inside the event horizon, the familiar structure of spacetime begins to unravel. Directions are no longer intuitive, and the traditional notions of up, down, left, and right lose meaning. The singularity is not just a point in space. It is a destination in spacetime, a line that all matter inevitably approaches. Every particle, every photon, every strand of energy is drawn toward this ultimate convergence. Following paths determined by the curvature of space-time itself, the physics inside the black hole is governed by both general relativity and quantum mechanics, a combination that challenges our current understanding. Classical general relativity predicts an infinitely dense singularity at the core, where curvature and gravity become infinite. Quantum effects, however, suggest that the singularity may be smoothed or replaced by exotic structures. Like a Planck star-theorized object where quantum pressure halts complete collapse. These ideas remain speculative but indicate that black holes are far more complex than a simple point of destruction. One of the most profound questions concerns the fate of information falling into a black hole. Classical physics suggests that once matter crosses the event horizon, all information about its state is lost. Quantum mechanics, however, forbids such destruction. The information paradox is at the heart of modern theoretical physics. Some theories propose that information is preserved at the event horizon in a holographic form, encoded in 2 dimensions, but representing the full 3-dimensional interior. Others speculate that information may be transferred to another universe through a black hole's singularity or a hypothetical wormhole. Speculative physics also introduces the idea of alternate universes. If a black hole connects to another region of spacetime, matter entering it might not simply cease to exist, could emerge in a different universe, a separate cosmic domain with its own laws of physics. Though entirely theoretical, this notion transforms the black hole from a destructive endpoint into a gateway to new realities. The singularity, often perceived as a final abyss, might instead be a portal to the unknown. Inside a black hole, time behaves strangely. Gravitational time dilation accelerates as one approaches the singularity, stretching the perception of events relative to outside observers. In some theoretical models, a traveler might witness the entire history of the universe in a single instant, a mind-bending convergence of past, present, and future. Such effects are not merely speculative. Mathematics, they are a direct consequence of Einstein's equations under extreme conditions. The matter and energy inside the black hole are compressed to unimaginable densities. Stars, gas, and even light are trapped within the intense curvature of spacetime. This compression may also create conditions where exotic forms of matter arise, forms not observed elsewhere in the universe. Quark, gluon plasma, strange matter, or other unknown states could dominate near the singularity, offering a glimpse into physical regimes far beyond our terrestrial experience. Beyond the purely physical, black holes prompt profound philosophical reflection. What does it mean for matter, energy, or even consciousness to cross the event horizon? Is existence terminated, transformed, or transported elsewhere? Could awareness survive the extreme conditions near the singularity, or is it inevitably absorbed into the fabric of spacetime? Black holes challenge not only our understanding of physics, but also the boundaries of human imagination and perception. From the outside, black holes exert influence through gravitational waves, lensing, and accretion phenomena. But within, they remain largely unobservable. The interior is hidden from direct observation, making it a realm accessible only through theory, mathematics, and indirect inference. This duality, the observable and the hidden, the destructive and the transformative, defines the essence of black holes and makes them unparalleled cosmic ENAS. In summary, journeying inside a black hole is a voyage to the extremes of the universe. Space-time warps, matter is stretched and compressed, and the normal rules of physics dissolve into new regimes dominated by quantum and relativistic effects. The singularity represents both an end and a potential beginning, a point of ultimate mystery where reality itself is transformed. In the next part, we will explore theoretical experiences and speculative phenomena deeper within a black hole, including spaghettification, wormholes, and the potential for passage into new universes. As one moves deeper past the event horizon, the effects of gravity intensify to unimaginable extremes. The differential gravitational pull, which stretches objects along the axis pointing toward the singularity, becomes overwhelming. This stretching transforms matter into a thin, elongated Schaefer process known as spaghettification. Named for its uncanny resemblance to a piece of spaghetti, this phenomenon is a direct consequence of extreme tidal forces. In smaller black holes, spaghettification occurs rapidly. But in supermassive black holes, it may occur only near the singularity, providing a temporary, eerie sense of normality as one falls inward. Spaghettification is more than a physical distortion. It represents the fundamental warping of space-time. Space itself is stretched, and time behaves irregularly, producing conditions that defy everyday logic. For matter and energy, this environment is both destructive and transformative. Ordinary atomic and molecular structures are pulled apart, forcing particles into configurations that cannot exist elsewhere in the universe. It is a realm where physics, as humans experience it, begins to lose its familiar meaning beyond the immediate physical effects. The deeper interior of black holes raises tantalizing possibilities for wormholes and cosmic pathways. Einstein-Rosen bridges, or theoretical tunnels connecting distant regions of spacetime, may exist within the extreme curvature of a black hole. In this model, a singularity is not merely an endpoint. It is a nexus linking one part of the universe to another, or even to a different universe entirely. While entirely speculative, these ideas suggest that black holes could serve as natural cosmic gateways. Matter entering the singularity might, in theory, re-emerge in a distant region of spacetime, bypassing the ordinary constraints of travel. The concept of alternate universes emerges naturally from these possibilities. If black holes do connect to other universes, each singularity could serve as the seed of a separate reality. In this view, black holes are not just destructive entities, they are creative forces, potentially giving rise to entirely new domains of existence. Matter falling into a black hole may undergo a transformation, crossing from one cosmic reality to another. Although unobservable from our perspective, this idea provides a radical reinterpretation of the singularity as a bridge rather than a terminus. Time itself is cute. Time itself is profoundly affected within a black hole. As the singularity approaches, gravitational time dilation reaches its extreme. For an outside observer, the infalling object seems frozen in time at the horizon, while the traveler experiences moments flowing normally, or even accelerating in perception relative to the distant universe. Some theoretical models suggest that, near the singularity, it may be possible to perceive the entire history of the cosmos in an instant, where past, present, and future converge. This intersection of time and space highlights the profound difference between tally-no-ly difference between May's Ruby Kiss. Ruby Kiss, only Ruby Kiss, has the luxurious texture. That only sees luggy texture. That / maze. And leave like a color / using caltrap. Maze, coi gate, maze, exeri. You say, they see so 6k at 7, wizev. Reset. With you, gapred, I may it. We may it's all. Like to maggot so an upsec I sit to coax casitasus a secret guy is yislubs again subjective experience and external observation in extreme. Gravity, the intense compression inside a black hole, could also generate exotic states of matter. Ordinary atoms are torn apart under tidal forces. And atomic nuclei themselves may break down into quark-gluon plasma or other unfamiliar forms. These extreme conditions offer a laboratory for physics at its limits, providing clues about the fundamental behavior of matter under unimaginable densities. Some theorists speculate that entirely new physical laws or particle states could emerge in such environments, revealing hidden aspects of reality inaccessible elsewhere. Quantum effects play an additional role. The information paradox suggests that while matter may disappear behind the event horizon, its information is never truly lost. Some theories posit that information is encoded on the event horizon itself, in a two-dimensional holographic form. If this is true, the interior of a black hole may preserve a complete record of all ingested matter, even as it collapses toward the singularity. This radical idea suggests that black holes are not mere destructive voids, they are archives of the universe, holding secrets that bridge gravity, quantum mechanics, and cosmology. Speculative ideas extend further. Some physicists imagine that consciousness or awareness might persist in some form through the extreme environment inside a black hole, while no experimental evidence exists. This notion provokes philosophical inquiry about the nature of existence and perception under extreme conditions. Could the mind, like information, survive in an altered state? Could the singularity function as a passage, transforming matter and awareness rather than destroying them? Such questions remain open-ended, but emphasize the profound mystery of black hole interiors. Finally, black holes affect the universe on a grand scale. Their presence alters the trajectories of stars, shapes the formation of galaxies, and produces relativistic jets that distribute matter across interstellar space. Gravitational waves, created by black hole mergers, ripple through space-time, revealing the energy and dynamics of these cosmic giants. Inside the black hole, the same forces that drive these observable effects continue, amplifying the sense of awe and power inherent in these extraordinary objects. In summary, venturing deeper inside a black hole transforms our understanding of matter, time, and reality itself. Spaghettification illustrates the raw physical power, while wormholes and alternate universe theories open the door to speculative possibilities that challenge the limits of imagination. Extreme gravitational and quantum phenomena converge to create an environment unlike anything encountered elsewhere, a realm where destruction and creation, death and transformation converge in the ultimate cosmic paradox. In the next part, we will explore the singularity, ultimate fate, and theoretical journeys beyond, concluding our examination of what lies inside a black hole and reflecting on the philosophical, scientific, and imaginative implications of these cosmic enigmas. At the core of every black hole lies the singularity, a point where conventional physics collapses and density becomes effectively infinite. This is the ultimate destination of all matter and energy that crosses the event horizon. While classical general relativity predicts an infinitely small, infinitely dense point, quantum mechanics suggests that singularities may be more complex, potentially involving exotic forms of matter or even a new structure of space-time itself. Understanding the singularity remains one of the greatest challenges in physics, as it represents the boundary where our current laws of nature are pushed to their extreme limits. Approaching the singularity, matter undergoes extreme compression and tidal distortion. Ordinary atomic structures are torn apart. Subatomic particles are squeezed into unfamiliar configurations, and space-time itself stretches and folds. In smaller black holes, this process happens very rapidly, leaving little time for any meaningful physical interactions. In supermassive black holes, however, these effects may occur more gradually, allowing for a prolonged journey through the inner regions before encountering the singularity. This gradient in gravitational extremes highlights the vast diversity of black hole interiors. The singularity also raises profound theoretical questions about the fate of information. Quantum theory asserts that information cannot be destroyed, yet classical black hole models imply total obliteration. This conflict, known as the information paradox, has led to radical proposals such as the holographic principle, black hole complementarity, and even the idea that singularities might act as conduits to other universes. If information survives or emerges elsewhere, black holes could be far more than destructive endpoints. They might participate in the ongoing evolution of matter. energy, and even consciousness across the cosmos. Some speculative theories suggest that the singularity could be a gateway to alternate realities. The concept of a wormhole, or Einstein-Rosen bridge, proposes that a black hole may connect to another region of spacetime, or even an entirely separate universe. In this scenario, matter crossing the singularity is not destroyed, but transported into a new cosmic domain. Such possibilities, while highly theoretical, invite a reimagining of black holes as transitional spaces rather than final destinations. They hint at a universe far more interconnected and mysterious than previously imagined. Time behaves in extraordinary ways near the singularity. Gravitational time dilation stretches moments in relation to outside observers. Some theoretical models propose that a traveler might perceive the full history of the universe compressed into a single experience, or that time might effectively merge with space, creating a timeless, almost eternal interior. These effects challenge the very concept of causality and sequence, presenting a reality in which conventional understanding of past, present, and future is profoundly altered. Another possibility lies in the formation of new universes. If the extreme conditions at the singularity can spark a fresh expansion of space-time, each black hole could serve as the seed of a new cosmos. In this framework, black holes are not merely destructive, they are creative, generating fresh realms beyond our observational reach. This transformative view aligns with certain cosmological theories, suggesting that universes may emerge, evolve, and branch endlessly, with black holes as the crucibles of creation. The singularity also emphasizes the limits of human perception and knowledge. No information can escape directly from within the event horizon, leaving scientists reliant on indirect evidence and theoretical models. Gravitational waves, accretion, disk emissions, and interactions with nearby matter provide clues, but the interior remains fundamentally hidden. This inaccessibility highlights both the power and mystery of black holes, making them symbols of the universe's ultimate unknowns. Philosophically, the singularity prompts reflection on existence and transformation. What does it mean for matter, energy, or even consciousness to reach a point of infinite density? Are endings absolute, or do they represent transformation into something beyond comprehension? Some theoretical frameworks suggest that the singularity could preserve patterns, information, or even consciousness in altered forms, hinting at continuity beyond apparent destruction. Black holes, in this sense, challenge our deepest assumptions about life, death, and the persistence of reality. Finally, black holes inspire imagination and exploration. They are extreme laboratories for testing theories of physics, but also metaphors for the unknown. They confront us with questions about the limits of observation, the nature of reality, and the potential for existence beyond observable space and time. The journey inside a black hole, from the event horizon to the singularity, traverses realms of both destruction and speculation, blending scientific rigor with imaginative possibility. In conclusion, the interior of a black hole is a realm of extreme physics and profound mystery. Spaghettification, tidal forces, wormholes, time dilation, and singularities all challenge our understanding of the universe. Speculative theories hint at alternate realities, baby universes, and the preservation of information in ways that defy classical intuition. Black holes are not merely voids, they are cosmic crucibles where physics is pushed to its limits, and where the boundaries of existence itself may be redefined. For anyone contemplating what lies inside, the journey is as much a voyage of the mind as it is of physics, inviting reflection on the ultimate fate of matter, energy, and even consciousness in the cosmos. Falling into a black hole is one of the most extreme journeys imaginable, a voyage to the very edge of physical reality. From the outside, the experience begins long before reaching the event horizon. Observers would see the infalling objects slow, its light stretched to red and then infrared, fading as it nears the boundary. This optical illusion caused by gravitational redshift creates the perception of time slowing dramatically, as though the object is suspended forever at the brink. Yet for the traveler themselves, motion remains normal, and the inevitability of crossing the event horizon becomes a deeply personal experience. A journey into a region where the familiar laws of physics are warped beyond recognition as one approaches the black hole. Gravitational forces intensify. The difference in gravitational pull between one's feet and head becomes pronounced, stretching the body along the axis toward the singularity. This stretching, the well-known spaghettification, can be surprisingly gentle in supermassive black holes, allowing for a longer descent before extreme distortion occurs. In smaller black holes, the forces become deadly almost immediately, compressing and elongating matter into unrecognizable forms. The experience is both violent and sublime. Demonstrating the raw power of these cosmic phenomena, the journey also involves relativistic effects. Time dilation causes the traveler's perception of events to diverge from that of distant observers. To the outside universe, the infaller appears to slow and freeze at the horizon. Yet internally, time flows normally or even stretches in perception, depending on gravitational gradients. This separation between subjective and external observation highlights the fundamental strangeness of black holes. What is perceived from outside does not reflect the internal reality. Approaching the black hole, tidal forces dominate the experience. Matter, light, and even information are subjected to extreme distortions. Atomic structures can be torn apart, particles accelerated to near-light speeds, and energy transformed in unprecedented ways. The interior is a landscape of extreme physics, where conventional notions of structure, movement, and stability cease to apply. Even the concept of inside is challenged, as space-time itself curves to a degree that makes linear navigation impossible. Black holes also confront us with questions of consciousness and perception. If a human or any sentient being were to approach the event horizon, what would it feel? Could awareness persist under these extreme conditions? Would the mind perceive a gradual compression, a sudden obliteration, or a surreal merging with space-time itself? While purely speculative, these questions underscore the intersection of physics and philosophy, where the boundaries of reality are tested and the limits of human imagination are explored. The gravitational energy near a black hole is staggering. Falling into it releases immense kinetic energy, enough to generate relativistic jets and other high-energy phenomena if the black hole is active. Even for a passive fall, tidal heating and particle acceleration would create intense radiation, making survival in any conventional sense impossible. Yet the thought experiment is illuminating. It allows us to explore physics under extreme conditions, testing theories of gravity, quantum mechanics, and space-time behavior. Entering the event horizon is not merely a physical crossing, it is a conceptual threshold. Beyond this point, escape is impossible, and all paths lead toward the singularity. Yet the event horizon is not a solid surface or wall. There is no dramatic barrier. Rather, it is a region defined by the inexorable nature of gravity. Crossing it is silent, unseen, and absolute. Once passed, the journey is entirely inward, toward a realm where space and time converge in unimaginable ways. Theories of wormholes and alternate universes also enter this scenario. While speculative, they suggest that the singularity might not be the absolute end. A black hole could, in theory, be a portal transporting matter into another region of spacetime or even a new universe. These concepts remain beyond empirical testing, but highlight the tantalizing possibility that falling into a black hole is not solely destructive might represent transformation or passage to new realities approaching the singularity. Extreme curvature of spacetime dominates the experience. Paths of particles are curved inward, horizons fold upon themselves, and the familiar three-dimensional geometry of the universe dissolves. For a traveler, the universe outside becomes a distant, distorted vista, while gravity guides every motion toward the singularity. In this environment, physics, as understood in everyday life, is replaced by the raw mathematics of Einstein's equations at extreme scales, with quantum effects adding layers of complexity and unpredictability. In summary, approaching a black hole is a journey of extreme spaghettification. Tidal forces, relativistic time dilation, and the inexorable pull of the singularity. From the outside, the fall appears slow and frozen, yet internally, it is rapid and absolute. This paradox between perception and reality, coupled with the potential for exotic phenomena like wormholes or new universes, makes the experience both terrifying and fascinating. It is a journey into the ultimate unknown, a voyage that tests the boundaries of physics, imagination, and understanding. In the next part, we will explore the extreme interior, crossing the event horizon, surviving tidal forces, and the speculative possibilities for passage through the black hole into other regions or realities. Crossing the event horizon marks a turning point in the journey into a black hole. From the outside, the falling object appears frozen in time, slowly fading as light is redshifted beyond visibility. Yet for the traveler, there is no dramatic boundary, no flash of light or sudden wall. The crossing is silent, absolute, and irreversible. Beyond this point, every trajectory leads inward, and escape becomes impossible. It is a realm governed by extreme gravitational curvature, where familiar physics gives way to new rules and radical possibilities. Once inside, the reality of tidal forces becomes unavoidable. Gravity acts differently across every inch of space. The closer one gets to the singularity, the more pronounced these differences become, stretching the body or object along the direction of gravitational pull and compressing it along perpendicular axes. In smaller black holes, this spaghettification occurs almost instantly, while supermassive black holes may allow a traveler to survive initial descent without immediate extreme distortion. Still, the environment is lethal. Atomic structures themselves are pulled apart, and matter is transformed into energy in ways that challenge comprehension. Time behaves in extraordinary ways inside the event horizon. The external universe continues, but the traveler experiences an internal flow that diverges from outside perception. Time dilation reaches extremes. What seems like seconds for the traveler might correspond to centuries or millennia outside. In some theoretical models, the traveler may even perceive a compression of cosmic history, a mind-bending convergence of past, present, and future. This illustrates one of the most profound aspects of black holes. They decouple subjective experience from external reality in ways that challenge our understanding of causality. Despite these destructive forces, black holes invite speculation about alternative fates and survival scenarios. Some theoretical physics models suggest that exotic matter, quantum effects, or even the structure of space-time near the singularity could provide conditions wherein, for Machinant, hypothetically awareness persists. These are entirely speculative, but provide fertile ground for thought experiments. Could consciousness survive in some altered form? Could matter entering the singularity be transformed rather than destroyed? These questions sit at the intersection of physics, philosophy, and imagination. As the traveler moves inward, relativistic and quantum effects interact in increasingly complex ways. Hawking radiation, normally negligible at the scale of infalling matter, may influence particle behavior near the singularity. Quantum fluctuations could stabilize certain structures temporarily, creating environments unlike any elsewhere in the universe. The interface between general relativity and quantum mechanics, the very essence of extreme physics, is most pronounced here, revealing the limits of current understanding and hinting at the need for a unified theory. Wormhole. Theories and the concept of alternate universes also emerge within this extreme environment. If the singularity connects to another region of spacetime, matter crossing it might theoretically re-emerge elsewhere. Such a wormhole would act as a cosmic shortcut, bypassing ordinary distances and potentially linking entirely separate universes. While there is no experimental evidence for this, it transforms the idea of a black hole from a mere destructive endpoint into a potential gateway, a doorway to realms beyond observation. Spaghettification itself illustrates the transformative nature of extreme gravity. The stretching and compression of matter is not merely destructive, represents a complete reconfiguration of physical reality. At the subatomic level, particles may be forced into new arrangements or states of matter, producing exotic phenomena that are inaccessible anywhere else. In this sense, black holes are laboratories for the universe's most extreme experiments, where conventional rules break down and new behaviors emerge. In addition, black holes highlight the limits of observation and perception. No direct information escapes from inside the event horizon. Everything beyond this boundary is hidden from external detection. Scientists rely on indirect evidence gravitational waves, accretion disk emissions, and relativistic jets to infer what happens within. This inaccessibility reinforces the black hole's status as a cosmic enigma, a region of absolute mystery where theory dominates understanding and imagination fills the gaps. Finally, crossing a black hole is a philosophical as well as a physical journey. It challenges concepts of death, transformation, and continuity, while matter and energy are inevitably drawn toward the singularity. Speculative theories suggest that forms of continuity might exist, whether through information preservation, transformation into another universe, or emergence as exotic matter. Black holes confront us with the limits of comprehension, inviting reflection on the boundaries of existence, awareness, and cosmic reality itself. In summary, crossing the event horizon is both a literal and conceptual passage into the extreme. Spaghettification, tidal forces, time dilation, and quantum effects define the interior environment. The singularity represents both an end and a potential beginning, where matter and information undergo transformations beyond ordinary experience. Wormholes, alternate universes, and speculative survival scenarios stretch the imagination and hint at the profound mysteries that black holes embody. The journey inside is an exploration of extremes, a confrontation with the ultimate limits of physics, and an invitation to consider realities beyond the visible universe. In the next part, we will conclude this chapter with the ultimate fate of anything entering a black hole, speculative cosmic journeys, and the philosophical implications of venturing into these enigmatic realms. The ultimate fate of anything entering a black hole remains one of the most profound mysteries in physics. Classical general relativity predicts a singularity, a point of infinite density and curvature where all paths converge. For matter, energy, or even theoretical consciousness, this is an inescapable endpoint. Atomic and subatomic structures are torn apart, space-time itself collapses, and conventional physics loses its descriptive power. The singularity represents a boundary beyond which the known universe ceases to exist in any familiar form. Yet this classical view is challenged by quantum considerations. Quantum mechanics forbids the total destruction of information. This conflict between relativity and quantum theory has produced revolutionary ideas such as the holographic principle, black hole complementarity, and theories suggesting that black holes may act as conduits for information transfer to distant regions of spacetime or even entirely new universes. In these speculative frameworks, the singularity is not an absolute end, but a transformative stage, reshaping the matter and information that pass through it. One intriguing concept is that of wormholes or Einstein-Rosen bridges. In certain theoretical models, the singularity might serve as a bridge to another region of spacetime. Matter entering the black hole could potentially emerge elsewhere, bypassing the ordinary constraints of space and time. While entirely unproven, this idea challenges the notion of a black hole as purely destructive. Instead, it becomes a cosmic junction, a place where universes could, in theory, connect and exchange matter, energy, or even information. Time near the singularity behaves in ways that defy ordinary intuition. Gravitational time dilation stretches the flow of time relative to outside observers. Some models suggest that a traveler might perceive an accelerated or compressed sequence of events, perhaps even glimpsing the history or future of the universe. In this environment, the line between past, present, and future blurs, revealing the profound relativistic effects that dominate extreme gravity. Time is no longer a simple linear measure, but a dynamic component intertwined with the structure of space-time itself. The concept of alternate universes emerges naturally from these ideas. If black holes serve as gateways, they may create or connect to entirely new cosmic domains. Matter falling into the singularity could seed a fresh universe with its own laws of physics, offering a radical reinterpretation of black holes as both destructive and creative entities. Each singularity might then represent not an absolute end, but a transformative doorway, giving rise to novel realities beyond observational reach. Philosophically, entering a black hole challenges our understanding of existence, consciousness, and the nature of reality. What does it mean for matter or awareness to traverse a point of infinite density? Could some form of continuity persist, even in altered or abstracted forms? Black holes push us to confront fundamental questions. Are endings absolute, or do they represent a transformation into something beyond human comprehension? Could the singularity itself be a crucible for creation, rather than mere obliteration? For hypothetical travelers, survival is impossible in conventional terms. Yet black holes offer an unparalleled exploration of physics. Spaghettification, tidal forces, and extreme curvature reveal the limits of matter and energy. The interior becomes a laboratory for testing the extremes of relativity, quantum mechanics, and space-time geometry, even without physical survival. The thought experiments illuminate the universe's deepest laws and encourage imagination to stretch alongside theoretical inquiry. Black holes also leave observable imprints on the cosmos, indirectly revealing their inner workings. Gravitational waves from merging black holes, relativistic jets from accretion processes, and interactions with nearby stars provide critical information. These phenomena hint at the dynamics inside, though the interior remains forever hidden from direct view. This duality, observable influence outside and concealed mystery inside, a discourse their enigmatic power. In considering black holes, one must also confront their symbolic and metaphysical implications. They represent both destruction and transformation, endings and potential beginnings. They are natural laboratories, philosophical provocations, and cosmic gateways all at once. They force us to question the nature of matter, energy, information, and even consciousness under conditions far beyond ordinary experience. Black holes are not simply voids, they are thresholds, testing the boundaries of what is knowable, imaginable, and possible. In conclusion, the journey into a black hole is simultaneously literal, scientific, and philosophical, crossing the event horizon, enduring tidal forces, and approaching the singularity reveal extremes of gravity, matter, and time. Speculative theories, wormholes, alternate universes, and information preservations suggest possibilities beyond destruction, hinting at transformation or passage into new realities. Black holes challenge our deepest intuitions and invite reflection on existence itself. To enter one is to confront the ultimate unknown, to experience the limits of the universe firsthand. and to ponder realities that stretch beyond comprehension. Black holes are not merely destructive phenomena. They are fundamental architects of the cosmos, shaping the structure, evolution, and ultimate fate of galaxies and the universe itself. Their gravitational influence extends far beyond their immediate surroundings, orchestrating the motion of stars, guiding the formation of stellar clusters, and regulating the dynamics of galactic centers. Supermassive black holes, residing in the cores of galaxies, act as gravitational anchors around which billions of stars rotate, stabilizing galactic structures over billions of years, in addition to stabilizing galaxies. Black holes influence the formation and evolution of stars. Gas and dust clouds under the pull of gravity collapse to form new stars. Black holes can trigger or suppress star formation depending on their activity. High-energy jets emitted by active black holes can compress interstellar gas in some regions, sparking the birth of stars, while in other areas, these jets can disperse matter, suppressing star formation. This duality shows that black holes are both creators and regulators, orchestrating cosmic processes on scales unimaginable to human perception. Black holes also play a role in galactic collisions and mergers. When galaxies collide, their central black holes interact, sometimes merging into even larger supermassive black holes. These mergers generate intense bursts of gravitational waves, rippling across spacetime, carrying information about cosmic evolution. The mergers influence the distribution of stars, gas, and dark matter, shaping the growth and architecture of galaxies for billions of years. In this sense, black holes act as cosmic engineers, influencing not only the structure of individual galaxies, but the architecture of the universe itself. The concept of cosmic recycling further illustrates their influence. Stars collapse into black holes, which in turn regulate the creation of new stars. Matter that falls into black holes may eventually be redistributed via jets or radiation, contributing to the ongoing cycle of matter and energy in galaxies. In this framework, black holes are not just endpoints, they are active participants in the evolution of matter, energy, and the large-scale structure of the cosmos. On an even grander scale, black holes affect the ultimate fate of the universe. Theories such as the heat death or the Big Freeze predict that the universe will continue expanding until stars burn out and matter is dispersed. Black holes, as long-lived entities, may persist far longer than ordinary stars, gradually evaporating through Hawking radiation over unimaginable timescales. This slow evaporation process transforms them into sources of radiation, slowly returning matter and energy to the universe and influencing its ultimate thermodynamic. State black holes also connect to speculative ideas about the multiverse. If black holes give rise to new universes via singularities acting as cosmic seeds, they may serve as mechanisms for ongoing cosmic creation. Each black hole could represent a branching point, generating new domains of existence. While unproven, this concept radically reimagines the role of black holes from destructive voids to engines of cosmic generation, potentially giving rise to universes with unique laws of physics and structures. The energy emitted by black holes, particularly through accretion disks and relativistic jets, demonstrates their dynamic power. As matter spirals into the black hole, gravitational energy is converted into intense radiation, sometimes outshining entire galaxies. This energy release not only affects nearby star formation, but also contributes to the cosmic background radiation that pervades the universe. Black holes, therefore, are not passive voids, they are active energy sources, shaping the thermal and dynamic environment of their surroundings. Furthermore, black holes play a role in cosmic balance. They mediate the distribution of angular momentum, mass, and energy within galaxies, influencing the movement of stars and interstellar matter. Without black holes, galaxies might lack the gravitational anchors necessary for long-term stability. leading to chaotic distributions of matter. Their presence ensures a delicate balance, allowing galaxies to maintain structure over billions of years, guiding the cosmic evolution from chaos toward order. In contemplating the long-term evolution of the universe, black holes may ultimately outlast all ordinary matter. While stars fade and galaxies disperse, supermassive black holes persist, slowly evaporating over timescales vastly exceeding the current age of the universe. In a universe dominated by these remnants, black holes would be the final witnesses to cosmic history, containing within their depths the record of billions of years of evolution, mergers, and transformations. They are, in this sense, the universe's ultimate archivists, preserving information about its past long after most other structures have vanished. In summary, black holes are much more than cosmic vacuums. They are architects, regulators, and potential progenitors of universes. They shape galaxies, influence star formation, guide mergers, and may even contribute to the creation of new realities. From their gravitational pull to their energy emissions, black holes actively participate in the ongoing evolution of the universe, playing a central role in its past, present, and future. As both destroyers and creators, they exemplify the duality of cosmic power, embodying forces that both end and generate, consume and catalyze, transforming the universe on every scale. In the next part, we will explore the interplay between black holes, dark energy, and the long-term cosmic future, considering how these enigmatic objects may influence the ultimate destiny of all existence. The universe is expanding, and this expansion is accelerating due to a mysterious force known as dark energy. Black holes, while immensely dense and gravitationally dominant locally, are still subject to this cosmic acceleration. Over billions of years, galaxies may drift apart, and the influence of dark energy may separate even the largest structures. In this scenario, black holes become isolated cosmic islands, slowly consuming what remains in their vicinity while the universe expands around them, eventually leaving them as solitary sentinels in an ever-growing void. As the universe continues its expansion, black holes play a paradoxical role. On one hand, they consume matter, regulating the distribution of mass within galaxies. On the other, their long-term evaporation through Hawking radiation may slowly return energy and particles to an increasingly empty cosmos over unimaginable timescales. This process contributes to the thermodynamic evolution of the universe, subtly counteracting the dispersal of energy caused by cosmic expansion. Black holes thus act as both sinks and sources of energy, shaping the universe on a scale far beyond human perception. The ultimate fate of matter in a universe dominated by black holes raises profound questions. Once stars have exhausted their fuel and galaxies have dispersed, black holes remain as the primary repositories of mass and energy. As they evaporate, they radiate energy back into space in the form of photons and subatomic particles. This slow trickle of energy contributes to a heat death, where the universe reaches a state of maximum entropy, uniform temperature, and minimal usable energy. Even in this bleak scenario, black holes leave a legacy. They regulate the flow of matter and energy over cosmic timescales and shape the universe's ultimate thermal equilibrium. Speculative theories suggest that black holes may also seed new universes. If singularities can generate space-time expansion, each black hole could give rise to a separate universe with its own laws of physics. While entirely theoretical, this possibility transforms black holes from mere destructive agents into cosmic creators, implying a multiverse in which black holes continually generate new realities. This idea offers a profound perspective on the role of black holes. They are not only shaping the observable universe, but potentially contributing to an endless chain of universes, each birthed from the depths of singularities. The relationship between black holes and dark energy remains a subject of ongoing research. Some models propose that black holes could interact with dark energy in subtle ways, influencing the rate of cosmic expansion locally or modifying the behavior of nearby matter. While these effects are not yet empirically confirmed, they suggest that black holes may be intimately connected with the universe's most enigmatic forces, participating in the dynamics that will ultimately dictate the cosmos's fate in a universe dominated by black holes and dark energy. Time itself becomes a factor of immense consequence. With galaxies dispersed and stars extinguished, black holes persist as the final active structures governing local spacetime and gravitational interactions. Their eventual evaporation over timescales trillions of times longer than the current age of the universe will mark the gradual dissipation of organized energy. In this cosmic endgame, black holes serve as both the last engines of activity and the ultimate witnesses to the universe's history. Black holes also pose questions about the limits of observation and knowledge. Even in the distant future, when the universe becomes dark and cold, remnants of black holes may encode information about cosmic history, effectively serving as time capsules. Gravitational waves from black hole interactions, Hawking radiation, and other subtle signals could provide clues about the universe's past, even when traditional structures have disappeared. In this sense, black holes preserve knowledge, acting as archival beacons across time. Philosophically, black holes challenge our perception of cosmic permanence. They are simultaneously destructive and generative, consuming matter while potentially initiating new realms of existence. Their role in the universe highlights the interplay between chaos and order, creation and annihilation. Black holes remind us that the cosmos is not static, but a dynamic arena of transformation, where even the most extreme phenomena contribute to the ongoing story of existence. Finally, black holes offer a unique perspective on human understanding of cosmic destiny. Observing and theorizing about black holes pushes the boundaries of physics, mathematics, and imagination. They compel us to consider the long-term evolution of the universe, the nature of spacetime, and the potential for realities beyond our own. In studying these cosmic titans, we confront the limits of knowledge, explore the ultimate fate of matter and energy, and glimpse the profound interconnectedness of all things. In summary, black holes are central to the universe's long-term future. Through their consumption of matter, influence on galaxies, emission of energy, and potential for seeding new universes, they shape the cosmos across unimaginable timescales. Coupled with dark energy, they participate in the universe's expansion, eventual entropy, and the ultimate thermal and structural equilibrium. Far from passive voids, black holes are dynamic agents of cosmic evolution, bridging destruction and creation, chaos and order, and guiding the universe toward its final state. In the next part, we will explore the philosophical and speculative implications of black holes as cosmic endpoints, gateways, and potential architects of multiple universes. Completing the chapter, as we contemplate the future of the universe, black holes emerge as both literal and metaphorical focal points for cosmic reflection. Their existence challenges our understanding of space, time, and the limits of knowledge. While their gravitational pull consumes matter, their role in the evolution of galaxies, the regulation of energy, and potential connections to other universes reveals a duality of destruction and creation. Black holes are not merely endpoints, they are cosmic laboratories, testing the boundaries of physics, imagination, and philosophy alike. Philosophically, black holes invite questions about the nature of endings and beginnings. When matter falls into a black hole, classical physics suggests a finality, irreversible collapse into a singularity. Yet speculative theories propose that this apparent destruction may conceal a transformation. Information, energy, or even space-time structures could be preserved or redirected, potentially seeding new regions of the cosmos. In this view, Each black hole embodies both an end and a beginning, a convergence of annihilation and creation, reflecting a profound symmetry at the heart of existence. The concept of cosmic continuity also emerges. While individual stars and galaxies have finite lifespans, black holes may persist across timescales far beyond human comprehension. Their evaporation through Hawking radiation occurs over durations trillions of times longer than the universe's current age, suggesting that black holes serve as enduring witnesses to cosmic history. In this way, black holes provide continuity, preserving the echoes of creation, the record of cosmic evolution, and the potential for future universes long after ordinary structures have. Faded black holes also illuminate the interconnectedness of all cosmic phenomena. From regulating star formation and galactic dynamics to generating gravitational waves and potentially linking to other universes, their influence permeates the cosmos. They remind us that even phenomena that seem destructive or isolated are woven into the fabric of the universe, shaping its evolution and connecting distant events in ways that challenge linear causality. This interconnectedness underscores the elegance and complexity of cosmic architecture, where extremes of gravity, matter, and energy are harmonized in a dynamic, evolving system. Speculative scenarios elevate this reflection further. If black holes act as gateways to other regions of space-time or entirely new universes, they transform our understanding of existence. Each black hole could represent a portal, a cosmic embryo generating novel realities. In such a framework, black holes are not endpoints of matter or energy, but engines of cosmic proliferation, continuously creating and transforming, linking the observable universe to a vast multiverse. This idea, while unproven, encourages a radical rethinking of the cosmos as an ongoing process of birth, death, and renewal. The relationship between black holes and consciousness also invites philosophical inquiry. If matter or information entering a black hole is preserved in some form, whether through physical transformation, quantum encoding, or linkage to other universes, what implications might this have for awareness, memory, or identity? These questions extend beyond physics into metaphysics, suggesting that black holes may influence not only the material universe but also the nature of perception, continuity, and existence itself in practical terms. Black holes challenge our methods of observation and inference. No direct probe can survive beyond the event horizon. Yet, we gather knowledge through indirect effects: accretion disks, relativistic jets, gravitational waves, and the behavior of nearby matter. These observations reveal patterns, forces, and histories that are otherwise hidden, illustrating the power of deduction and imagination. The study of black holes demonstrates the interplay between the observable and the unknowable, encouraging scientists to explore the limits of knowledge while acknowledging the profound mysteries that remain. From a cosmic perspective, black holes are ultimate arbiters of entropy and energy distribution. Their role in the thermodynamic evolution of the universe, absorbing matter, emitting Hawking radiation, and regulating galactic dynamics, frames them as central actors in the universe's long-term fate. Over trillions of years, they may govern the transition to a state of maximum entropy, guiding the universe toward a diffuse, energy-equilibrated equilibrium. In this sense, black holes are both destructive engines and regulators, shaping cosmic destiny over unimaginable timescales. Finally, black holes compel reflection on human understanding and imagination. They push the boundaries of theory, mathematics, and observation, inspiring new concepts in physics, cosmology, and philosophy. They illustrate that the universe operates on scales and with forces far beyond ordinary experience, challenging us to think beyond conventional notions of time, space, and matter. In contemplating black holes, we confront not only the universe's physical extremes, but also the limits of human perception, creativity, and understanding. In conclusion, Black holes are simultaneously endings and beginnings, destructive voids and cosmic creators, isolated entities and interconnected architects of the universe. Their influence spans galaxies, governs the flow of matter and energy, and may extend to multiple universes. They represent the ultimate extremes of physics and the profound mysteries of existence, shaping the universe across space, time, and possibly beyond. By studying and reflecting on black holes, we gain insight into the cosmos's past, present, and potential futures, confronting the ultimate questions of creation, destruction, and the nature of reality itself. Black holes have long fascinated scientists and philosophers alike, not only as cosmic sinks of matter and energy, but also as potential gateways to other universes. While conventional physics describes black holes as regions of space-time with gravitational pull so intense that nothing can escape, theoretical models suggest that they may also act as bridges or conduits to other regions of space-time. These ideas emerge at the intersection of general relativity, quantum mechanics, and speculative cosmology, inviting a radical reconsideration of the role black holes play in the cosmos. At the heart of this speculation is the singularity, the point at the center of a black hole where density becomes infinite and conventional laws of physics break down. In classical general relativity, the singularity represents an ultimate boundary, all matter and information collapsing to a point, inescapable and permanent. Yet when quantum mechanics is introduced, the picture becomes less absolute. Some physicists propose that singularities may serve as connective nodes in spacetime, linking our universe to other realms. These ideas are deeply theoretical, but they suggest that black holes may not be final destinations. Instead, they could be portals to alternate universes or dimensions. One of the most influential frameworks supporting this concept is the Einstein-Rosen bridge, or wormhole. Originally proposed in the 1930s, a wormhole is a theoretical passage connecting to separate points in spacetime. In certain models, black holes could form one end of such a bridge, with the singularity acting as the junction. Matter entering a black hole could theoretically traverse the wormhole and emerge in a distant location or even a completely separate universe with potentially different physical laws. While wormholes have never been observed, their mathematical consistency within Einstein's equations allows physicists to explore these tantalizing possibilities. Quantum theories add further intrigue. The holographic principle, for example, suggests that information absorbed by a black hole is not destroyed but encoded on its surface. This principle hints at the preservation of information, even in extreme conditions, raising the possibility that matter entering a black hole could be transformed rather than annihilated. Such transformations might involve transitions into different regions of spacetime or alternate realities, lending theoretical plausibility to the idea that black holes are more than destructive voids. They could be engines of cosmic transformation. Another speculative approach involves multiverse cosmology. In some interpretations of inflationary theory, our universe is one of many, each forming from quantum fluctuations in a primordial energy field. Black holes could serve as natural conduits between these universes, their singularities acting as tunnels through the fabric of spacetime. Matter and energy passing through might contribute to the birth or sustenance of other universes, creating a network of interconnected realities. While entirely theoretical, this framework elevates black holes from local phenomena to cosmic architects, potentially shaping not only our universe, but an entire multiverse. The idea of traversable black holes also arises in these discussions. Conventional black holes are not survivable, and the immense tidal forces near the singularity would destroy any conventional matter. However, in certain theoretical models, exotic matter with negative energy density could stabilize a wormhole, preventing collapse and allowing passage, while such matter has not been discovered. Its hypothetical existence provides a conceptual foundation for black holes functioning as gateways. If possible, a traveler might move through a black hole and emerge in an entirely different cosmic environment, a scenario that stretches both imagination and physics. Observational hints, while indirect, further motivate these ideas. The detection of gravitational waves from black hole mergers has confirmed predictions of general relativity with remarkable precision, demonstrating that black holes behave as predicted by extreme space-time curvature models. These observations, combined with the study of high-energy phenomena around black holes, such as relativistic jets and accretion disk emissions, suggest that black holes interact with their surroundings in ways that could influence other regions of space-time. Even if direct traversal remains speculative, the concept of black holes as portals challenges our understanding of space, time, and causality. Traditional physics treats cause and effect as linear, but wormhole models imply nonlinear connections between distant regions. Events in one universe could theoretically influence another, mediated by a black hole. This opens philosophical and theoretical questions about determinism, free will, and the continuity of information. If black holes serve as cosmic connectors, they might function as conduits for information transfer across vast distances or even between universes, blurring the distinction between destruction and creation. Finally, black holes as gateways emphasize the limits of human perception and observation. No probe can survive beyond the event horizon, and the interior remains hidden from view. Yet the laws of physics allow us to model these interiors mathematically, providing a window into possibilities otherwise inaccessible. By exploring black holes through theory, mathematics, and indirect observation, scientists push the boundaries of knowledge, contemplating not only the fate of matter and energy, but also the potential existence of realities beyond our word. Observable universe. In summary, theoretical physics provides several foundations for considering black holes as gateways to other universes. The singularity, Einstein-Rosen bridges, the holographic principle, multiverse cosmology, and exotic matter all contribute to a conceptual framework in which black holes are not simply endpoints, but dynamic structures with transformative potential. They challenge our understanding of causality, space, and time, inviting exploration into realities that may lie beyond direct observation. While empirical evidence remains elusive, the intellectual and imaginative implications of black holes as portals are profound, offering one of the most compelling frontiers in modern cosmology. While the idea of black holes as gateways to other universes remains speculative, theoretical physics provides several intriguing frameworks that suggest how such cosmic travel might be possible. These models emerge from the intersection of general relativity, quantum mechanics, and cosmological theory, each offering a unique perspective on how singularities could link different regions of space-time or even separate universes. One prominent framework is the traversable wormhole concept. Unlike classical black holes, which destroy anything entering the event horizon, a traversable wormhole would allow matter to pass from one region of spacetime to another. To remain stable and avoid collapse, these wormholes require exotic matter hypothetical material with negative energy density that counteracts gravitational forces. If such matter exists, it could prevent the wormhole from pinching off, creating a stable passage through the singularity. In principle, this could allow a traveler to enter one end of the black hole and emerge in a distant location, or an entirely new universe. The Einstein-Rosen bridge remains central to this discussion. Originally derived from solutions to Einstein's equations of general relativity, these bridges describe connections between two separate regions of spacetime. Classical versions are unstable and non-traversable, collapsing too quickly for anything to pass through. However, Modern theoretical models suggest that quantum effects could stabilize these bridges under certain conditions, providing hypothetical mechanisms for inter-universal travel. While no empirical evidence exists, the mathematical consistency of these solutions encourages physicists to explore their implications. Quantum mechanics introduces additional possibilities. The holographic principle implies that information absorbed by a black hole is preserved on its surface rather than destroyed. This suggests that matter entering a black hole could undergo a transformation rather than annihilation. Some theories propose that this information could emerge elsewhere, either in distant regions of our universe or in alternate realities. In such a scenario, black holes function as cosmic information processors, reshaping matter and energy and potentially linking disparate universes in ways not immediately observable. Another speculative avenue involves baby universes. In certain cosmological models, the singularity of a black hole could give rise to a new expanding universe. Matter and energy entering the black hole may seed this universe, creating a cosmos with its own physical laws. While the parent universe may lose direct access to this new region, the concept positions black holes as engines of cosmic proliferation rather than mere endpoints. This theory reimagines black holes as creative forces, contributing to a multiverse in which each singularity represents a nascent reality. The ADS CFT correspondence from string theory also provides a potential framework. This principle relates a gravitational system in a higher dimensional spacetime, like a black hole, to a lower dimensional quantum field theory on its boundary. In this view, the interior of a black hole may encode information in ways that preserve quantum coherence, hinting at pathways through which matter or information could transition to other regions of spacetime. While highly theoretical, this correspondence offers a mathematically rigorous approach to conceptualizing black holes as more than destructive voids. Practical challenges, however, remain staggering. The immense tidal forces near a singularity commonly known as spaghettification would stretch and compress matter to extreme degrees. Any attempt at physical traversal requires mechanisms to withstand or circumvent these forces. Exotic matter or advanced technology beyond human comprehension might hypothetically stabilize the journey, but such conditions are purely theoretical. Moreover, the passage through a wormhole or singularity would confront the traveler with profound temporal and spatial distortions, including extreme gravitational time dilation. Time itself may flow differently inside the black hole, further complicating any hypothetical journey. Despite these challenges, black holes as portals remain an intellectually rich area of study. Observations of gravitational waves and high-energy phenomena near black holes provide indirect evidence of their dynamic behavior, including mergers that could hypothetically generate temporary or unstable connections in spacetime. Accretion disks and relativistic jets reveal immense energy transformations, hinting at processes that may influence distant regions or dimensions. While we cannot yet observe inter-universal travel, these phenomena underscore the active and transformative nature of black holes. Speculative physics also entertains causal connections between universes. If black holes act as conduits, events in one universe could theoretically affect conditions in another, mediated through singularities or wormhole pathways. This challenges classical notions of causality and locality, suggesting that black holes may serve as bridges not only for matter and energy, but also for information, potentially linking realities in ways that defy conventional physics. Such possibilities encourage imaginative exploration and philosophical reflection on the nature of existence. In conclusion, theoretical models provide multiple frameworks for considering black holes as gateways to other universes. Traversable wormholes, Einstein-Rosen bridges, holographic encoding, baby universes, and string theory correspondences all hint at mechanisms by which black holes could connect disparate regions of spacetime or even distinct universes, while practical traversal remains beyond reach. These ideas highlight the potential of black holes as transformative cosmic structures, reshaping matter, energy, and information on scales both immense and profound. The idea of black holes as portals to other universes extends far beyond physics, entering the realm of philosophy, metaphysics, and imaginative speculation. If black holes are not mere endpoints but potential gateways, they compel us to reconsider the nature of existence, causality, and the limits of human understanding. The philosophical implications are profound, challenging conventional notions of beginnings, endings, and the very structure of reality. At the heart of this reflection is the concept of cosmic continuity. Traditional cosmology treats black holes as terminators of matter and energy. Anything crossing the event horizon is lost forever. However, if black holes connect to other universes, matter and information are not annihilated but transformed or redirected. This challenges the finality of death, decay, and destruction in a cosmic sense. Black holes may represent processes of renewal, suggesting that endings in one universe could become beginnings in another, weaving a continuous, evolving tapestry of existence across multiple realities. This perspective also reshapes our understanding of cause and effect. Classical physics assumes linear causality, causes precede effects within a single space-time continuum. Black holes as portals, however, imply nonlinear and non-local interactions, where events in one universe might influence another through singularities or wormhole connections. Such a framework challenges the limits of determinism, opening the possibility that the universe or multiverse is far more interconnected and dynamic than previously imagined. Philosophically, this raises questions about free will, the propagation of information, and the scope of cosmic influence. Another profound implication involves the preservation of knowledge and information. If matter entering a black hole is encoded or transformed, then black holes act as repositories or conduits of cosmic memory. The universe's history encoded in the interactions of particles, energy, and space-time geometry may not be lost, but redistributed. In a multiverse scenario, each black hole could carry the potential to seed new universes, preserving traces of the parent universe's structure, laws, or events. This positions black holes as archivists of existence, safeguarding continuity across cosmic scales that dwarf human comprehension. Speculative thought also introduces the concept of cosmic creativity. Black holes may function as engines of transformation, generating new universes with distinct physical laws and structures. This frames the universe not as a static stage, but as a living, evolving system in which singularities catalyze the birth of new realms. In this light, black holes are not only destructive, but profoundly generative, embodying the duality of annihilation and creation. Philosophically, this aligns with ideas of eternal recurrence, cyclic cosmology, and the interdependence of destruction and genesis. The concept of existential perspective is equally compelling. Black holes, as potential gateways, remind us of our limitations as observers confined to a single space-time. They highlight the humility required in understanding the cosmos, suggesting that vast realms, processes, and structures may exist entirely beyond direct human perception. Yet, through mathematics, theory, and observation of indirect effects, we glimpse the extraordinary possibility that black holes connect realities in ways that challenge imagination. This duality between observable limits and theoretical horizons defines the philosophical allure of black holes. Speculative fiction often explores these themes, envisioning black holes as portals to alternate dimensions or universes. While imaginative, these narratives parallel scientific speculation, offering conceptual experiments for understanding causality, identity, and cosmic architecture. If black holes truly link universes, then human exploration, even in principle, could extend beyond our observable cosmos, transforming existential questions into active inquiries about cosmic navigation, survival, and continuity. Finally, black holes as portals prompt reflection on the nature of infinity and boundaries. A singularity represents the convergence of infinite density and space-time curvature, point where conventional laws break down. If singularities connect to other universes, they serve as thresholds beyond which the familiar concepts of space, time, and matter no longer apply. These thresholds challenge both science and philosophy, demanding new ways of thinking about reality, existence, and the ultimate potential of the cosmos. In conclusion, the notion of black holes as gateways to other universes is both scientifically provocative and philosophically profound. They transform our understanding of endings and beginnings, causality, information preservation, and cosmic creativity. While empirical evidence remains elusive, theoretical frameworks, including traversable wormholes, holographic principles, and multiverse cosmology, afford conceptual foundations for imagining black holes as dynamic participants in a multiversal network. By contemplating black holes as portals, we confront the limits of observation, the potential for interuniversal continuity, and the vast horizons of cosmic possibility. They are simultaneously destroyers and creators, endpoints and beginnings, local phenomena and universal connectors. Through them, the universe challenges us to expand our understanding of reality, to embrace both scientific rigor and imaginative speculation, and to recognize that even the darkest voids may harbor the seeds of new realms. Thus, black holes stand as monuments to cosmic mystery, bridging the known and the unknown, the observable and the theoretical, the finite and the infinite. They invite us to ponder not only what lies within the depths of these enigmatic objects, but also what lies beyond to cross the boundaries of our universe and into the vast potential of all possible realities. Black holes are among the most extreme objects in the universe. Their gravity is so powerful that even light cannot escape, earning them the name black. But how strong is their influence? And could black holes ever consume entire galaxies or even the universe itself? To answer this, we must explore their gravitational behavior, the distribution of matter in the cosmos, and the limits imposed by cosmic expansion. A black hole's gravitational pull is most intense near its event horizon, the boundary beyond which escape is impossible. Anything crossing this boundary is inexorably drawn toward the singularity at the core. The singularity is a point of infinite density, where classical physics breaks down and all matter is compressed to zero volume. The immediate vicinity of a black hole is thus a region of extreme space-time curvature, warping the fabric of the universe in ways that defy ordinary intuition. The size and mass of a black hole are crucial in determining its reach. Stellar mass black holes, formed from the collapse of massive stars, have masses ranging from a few to tens of solar masses. While immensely dense, their gravitational influence is limited to the immediate neighborhood of their stellar system. Supermassive black holes, however, are millions or even billions of times the mass of the Sun, anchoring the centers of galaxies. Their influence extends across tens of thousands of light-years, controlling the orbits of stars and regulating the dynamics of entire galactic cores. Despite their immense gravity, black holes do not actively suck in matter across the cosmos. Objects must venture close enough to be drawn in by gravitational attraction. In this sense, the universe is largely safe from wholesale consumption by black holes. Even the largest supermassive black holes are confined by the distribution of matter in galaxies and the vast distances separating them. Space is overwhelmingly empty, meaning that most matter never comes close enough to fall in. Cosmic expansion adds another critical factor. The universe is growing at an accelerating rate due to dark energy, pushing galaxies away from each other over vast distances. This expansion counteracts the gravitational pull of black holes on the largest scales, preventing them from merging into a single universe-consuming entity. While black holes dominate locally, they are powerless against the vast, accelerating cosmic void. In other words, the universe is expanding faster than even the mightiest black holes can reach. Nevertheless, black holes can influence cosmic structure over time. By consuming gas, dust, and stars, they regulate star formation, galactic evolution, and energy distribution. In a sense, they act as cosmic sculptors, shaping the architecture of galaxies without threatening the universe at large. Even in extreme scenarios such as galaxy collisions or mergers, the result is the growth of larger black holes, not the total annihilation of surrounding space. Another consideration is the long-term evolution of black holes themselves. According to Hawking radiation, black holes slowly emit energy over astronomical timescales, eventually evaporating completely. This process takes trillions of years for supermassive black holes. Far from devouring everything, they gradually release what they have absorbed back into the cosmos. Over the lifespan of the universe, this mechanism ensures that black holes cannot indefinitely accumulate matter, placing a natural limit on their power. Theoretical extremes, such as a universe entirely composed of matter collapsing into a single black hole, are intriguing but highly speculative. In reality, the expansion of space, the distribution of matter, and the finite lifespan of stars and black holes prevents such scenarios. Even if multiple black holes were to merge, the process would be local rather than universal. The concept of a black hole swallowing the universe remains a dramatic thought experiment rather than a physical likelihood. Philosophically, black holes embody the tension between local dominance and universal limitation. They demonstrate the extremes of gravity and the destructive potential of singularities. Yet they are bound by the laws of physics and cosmic scale. Their power is immense but not infinite, highlighting the delicate balance between force, distance, and expansion that governs the cosmos. In summary, black holes are gravitational titans capable of consuming matter within galaxies and regulating cosmic structure. But they are not capable of devouring the universe itself. Their influence is local and constrained by cosmic expansion, matter distribution, and their own eventual evaporation. While awe-inspiring and terrifying, black holes are part of a universe governed by balance, limits, and expansive horizons far beyond their reach. In the next part, we will explore the potential scenarios in which black holes could threaten large-scale cosmic structures and the interplay with dark energy and galactic evolution, deepening our understanding of their cosmic role. While black holes cannot consume the entire universe, their gravitational influence on local structures is profound. On galactic scales, supermassive black holes at the centers of galaxies control star orbits, regulate gas flows, and influence galactic evolution. Their immense gravity can trigger cosmic phenomena such as accretion disk emissions, relativistic jets, and gravitational waves from mergers, all of which impact surrounding matter across thousands of light-years. One potential threat lies in the scenario of galaxy collisions. When galaxies merge, their central black holes may eventually collide, forming an even larger supermassive black hole. During this process, enormous amounts of energy are released, and nearby stars may be ejected from the galactic core. Though dramatic, this is a localized event, and the universe at large remains unaffected. Even repeated galactic mergers would not alter the structure of the expanding universe itself. Another consideration is black hole clustering. Over billions of years, black holes can attract one another, forming larger, more massive entities. The resulting gravitational influence could dominate local regions of space, pulling in nearby matter more efficiently. However, cosmic expansion, fueled by dark energy, prevents black holes from merging across vast distances. as galaxies drift apart faster than gravity can pull them together. Most black holes remain isolated, limiting the possibility of creating a single, universe-spanning black hole. Dark energy plays a critical role in this cosmic balance, accounting for roughly 70% of the universe's energy content. Dark energy drives the accelerated expansion of space, pushing galaxies away from each other at increasing speeds. Even the most massive black holes cannot overcome this repulsive effect on a universal scale, while they dominate their immediate surroundings. The vast distances between galaxies grow ever larger, ensuring that black holes remain local titans rather than universal predators. Moreover, black holes themselves are subject to Hawking radiation, a process in which quantum effects near the event horizon cause them to slowly emit energy. Over unimaginable timescales, this results in the gradual evaporation of even the largest black holes. Consequently, black holes are not permanent cosmic vacuum cleaners. Their dominance is temporary, and the matter they consume may eventually be released back into the universe, maintaining a delicate cosmic equilibrium. Consider also tidal forces and the spaghettification effect. Objects approaching a black hole are stretched and compressed due to extreme gravitational gradients. While destructive on a local scale, these forces are confined to the immediate vicinity of the black hole. Stars, planets, and dust that stray too close may be consumed, but objects at safe distances remain untouched. Thus, black holes' ability to devour is spatially limited, emphasizing the contrast between local destruction and universal safety. Even in speculative scenarios involving primordial black holes or hypothetical ultramassive black holes, cosmic expansion and the sparse distribution of matter prevents universal consumption. Primordial black holes, which may have formed shortly after the Big Bang, are theorized to exist in a range of sizes, but their influence is mostly negligible on cosmological scales. The universe's matter is too diffuse and distances too vast for even these ancient black holes to threaten large-scale cosmic structure. In addition, the universe's entropy-driven evolution imposes further limitations. Over trillions of years, stars will burn out, galaxies will fade, and black holes will gradually evaporate. This slow march toward thermodynamic equilibrium ensures that the universe cannot be devoured in a catastrophic instant. Black holes act as regulators of energy and matter, not agents of cosmic annihilation. Philosophically, this interplay between black holes and cosmic expansion highlights the limits of power and reach. Black holes exemplify extremes of gravity and density, yet they operate within boundaries set by universal laws. Their immense local effects are dwarfed by the vastness and accelerating expansion of the cosmos, a reminder that even the most powerful forces have limits in a universe governed by structure, law, and scale. In conclusion, while black holes are capable of consuming stars, regulating galactic structure, and influencing local cosmic evolution, they are constrained by dark energy, cosmic expansion, and their own eventual evaporation. Their potential to devour is significant locally, but impossible on universal scales. Far from being harbingers of cosmic annihilation, black holes are key players in the universe's long-term evolution, balancing matter, energy, and entropy across space and time. While realistic physics indicates that black holes cannot consume the universe, considering extreme hypothetical scenarios can sharpen our understanding of cosmic limits and the scale of their power. One such scenario involves ultramassive black holes, far beyond the supermassive ones observed in galactic centers. If an ultramassive black hole were somehow formed from the merger of countless galactic cores, it could dominate a substantial portion of a supercluster. In such a region, stars and matter might be rapidly drawn in, creating a cosmic void around the black hole. However, this influence would remain local, constrained by intergalactic distances and the expansion of space. The universe as a whole would remain untouched, Another speculative scenario involves the Big Crunch, a hypothetical collapse of the universe under its own gravity. In this model, all matter and energy would eventually be drawn together, and black holes could merge into unimaginably massive singularities. Here, the boundaries between local and cosmic effects blur. However, current observations indicate that the universe is accelerating in expansion due to dark energy, making a Big Crunch unlikely. Instead of cosmic collapse, the universe seems destined for continued expansion, in which black holes grow slowly and evaporate over trillions of years, never threatening the universe itself beyond physics. Black holes challenge us philosophically, especially when considering limits of human comprehension. Their singularities represent points where space-time and density reach extremes beyond the grasp of conventional mathematics or observation. Even with advanced theory, our understanding remains indirect, relying on extrapolations, simulations, and the laws of physics in familiar regimes. This raises profound questions. How do we conceptualize forces and objects beyond experience? What does it mean to know something that defies observation? Black holes serve as metaphors for the edges of human knowledge titanic, forces whose nature is partially revealed but largely hidden. The destructive power of black holes also prompts reflection on the nature of cosmic balance. While they consume stars and shape galaxies, they also release energy, regulate star formation, and eventually evaporate, returning matter to the universe. They exemplify the duality of creation and destruction in the cosmos. This balance reminds us that even forces of immense power operate within natural limits, maintaining order and structure over scales far beyond human life. Black holes are destructive locally but constructive globally, orchestrating the evolution of galaxies and interstellar environments. Extreme scenarios involving hypothetical universe-consuming black holes illuminate not only the limitations of these objects but also the role of cosmic expansion and dark energy. Without accelerated expansion, gravitational forces could theoretically dominate larger regions, allowing black holes to merge and reshape local superclusters. Yet even in this extreme, they remain constrained spatially. They are giants confined to their neighborhoods, not universal predators. This underscores an essential lesson. Power in the universe is relative and bounded by the interplay of forces, distances, and physical laws. Philosophically, black holes also provoke contemplation about existence and impermanence. Every black hole is transient on cosmological timescales. Stars die, galaxies evolve, and even black holes themselves evaporate. The universe is dynamic, a theater of emergence and decay. Black holes, in this view, are not threats to existence, but participants in its cycles, illustrating how creation and destruction coexist in a vast, self-regulating system. They demonstrate that even the most formidable phenomena are part of a larger cosmic rhythm, bound by time, space, and universal law. In speculative fiction and thought experiments, black holes often symbolize ultimate destruction. Yet physics reminds us that they are local, extreme objects, influential yet constrained. They are reminders of the scale of the universe, the limits of control, and the awe-inspiring nature of forces far beyond human comprehension. Their study invites humility, curiosity, and reflection on the interconnectedness of cosmic systems. In conclusion, while the question, "Can black holes devour the universe?" evokes dramatic imagery, the scientific answer is clear: no. Local devastation is possible, cosmic shaping occurs, but the universe at large is safe from annihilation by black holes. Their influence, though immense in specific contexts, is bounded by cosmic expansion, dark energy, spatial distribution, and their own finite lifespans. Black holes serve as engines of transformation, not extinction. demonstrating the balance between creation and destruction on a galactic scale. Ultimately, black holes challenge human imagination, revealing extremes of physics while highlighting the resilience and vastness of the universe. They remind us that even objects of unimaginable density and power are part of a structured, dynamic cosmos, operating under laws that maintain balance across unfathomable scales. In studying them, we explore not only gravity and singularities, but also the profound philosophical questions about existence, power, and the limits of our understanding. Black holes, once purely theoretical, have long captured the human imagination. From the earliest predictions in the realm of general relativity to the first observational evidence of these cosmic enigmas, humanity's fascination with black holes reflects a deep desire to understand the universe's extremes. They symbolize both the limits of human knowledge and the audacious curiosity that drives science forward. The concept of a black hole emerged from Albert Einstein's general theory of relativity in 1915, which described how mass and energy curve space-time. Shortly afterward, Carl Schwarzschild discovered a solution to Einstein's equations, predicting the existence of regions where gravity becomes so intense that nothing, not even light, can escape. These dark stars, as they were initially called, were purely mathematical curiosities. Yet they laid the groundwork for modern astrophysics, humanity's quest to comprehend black holes, accelerated with the discovery of stellar phenomena that hinted at their presence. In the 1960s, astronomers observed X-ray emissions from binary star systems like Cygnus X1, suggesting a massive invisible companion pulling matter through gravity. These observations provided indirect evidence for black holes, transforming them from theoretical abstractions into objects with measurable influence. Black holes inspire curiosity not only for their gravitational might, but also for their philosophical implications. They challenge notions of time, space, and causality. The concept of an event horizon where time effectively stops for a falling observer forces humans to confront the limits of perception and understanding. For centuries, humanity has sought to peer into the unknown, and black holes represent the ultimate frontier, regions where conventional experience breaks down, and imagination is the only guide. The study of black holes has also driven technological and scientific innovation. Observing their effects requires extraordinary instruments, from radio telescopes detecting subtle gravitational waves to space-based observatories capturing X-rays emitted by accreting matter. Each advance in detection and measurement expands our ability to understand not only black holes, but also the broader universe, including galaxy formation, cosmic evolution, and the behavior of matter under extreme conditions. Black holes also engage the public imagination. Popular science books, documentaries, and films such as Interstellar have introduced millions to concepts like time dilation, spaghettification, and wormholes. These cultural representations blend scientific principles with creative storytelling, helping humanity conceptualize phenomena that are otherwise abstract and incomprehensible. They turn distant singularities into symbols of wonder, fear, and possibility, reflecting our innate desire to understand the cosmos and our place within it. Humanity's fascination with black holes is intertwined with the exploration of the unknown. Like ancient mariners mapping oceans or early astronomers charting stars, we push the boundaries of knowledge to understand extreme phenomena. Black holes exemplify this endeavor, demanding both intellectual rigor and imaginative courage. They represent the intersection of observation, theory, and speculation, a domain where mathematics meets philosophy and physics meets wonder. Moreover, black holes have inspired thought experiments that challenge conventional ideas about reality. For instance, physicists have pondered the information paradox, the question of whether information that falls into a black hole is lost forever or somehow preserved. These inquiries not only push theoretical physics forward, but also stimulate broader reflection on the nature of existence, knowledge, and the limits of comprehension. In contemplating black holes, humans confront questions about life, death, and the continuity of matter and energy across cosmic scales. The human connection to black holes is also personal and psychological. These cosmic objects evoke feelings of awe, insignificance, and curiosity simultaneously. They remind us of our smallness in the face of the universe's vastness. Yet they also inspire hope through study and observation. Humanity can uncover truths about phenomena billions of light years away, pushing the boundaries of understanding and revealing our capacity to grasp the unimaginable. Finally, black holes exemplify the interplay between risk and reward in exploration. Just as humanity has ventured into oceans, mountains, and outer space, studying these singularities involves navigating conceptual and technological challenges. The reward is knowledge and sight into the universe's most extreme environments, understanding of fundamental physics, and glimpses into the origins and fate of the cosmos. Black holes serve as both challenge and opportunity, symbolizing humanity's relentless pursuit of truth. In conclusion, the human fascination with black holes spans science, philosophy, culture, and psychology. They challenge our understanding of gravity, time, and matter while inspiring exploration, innovation, and imagination. Humanity's engagement with these cosmic mysteries exemplifies curiosity at its most profound, a desire not only to understand the universe, but also to confront its extremes, to embrace wonder, and to explore the boundaries of knowledge and imagination. Humanity's engagement with black holes extends beyond imagination and theory into practical observation and measurement. While black holes themselves emit no light, their presence is revealed indirectly through interactions with surrounding matter. By studying accretion disks, X-ray emissions, gravitational waves, and stellar motions, scientists have developed a detailed understanding of these extreme objects, allowing humanity to probe the universe's most mysterious regions. Accretion disks provide one of the most visible signs of a black hole's presence. Matter spiraling into a black hole heats up to millions of degrees due to friction and gravitational compression, emitting X-rays and gamma rays detectable by space telescopes. Observatories such as NASA's Chandra X-ray Observatory and ESA's Newton have captured these emissions, offering empirical evidence of black holes' influence on their surroundings. Observing these emissions allows scientists to measure the mass, spin, and other characteristics of black holes, effectively seeing what is otherwise invisible. Gravitational waves have opened a new window into black hole observation. First detected in 2015 by LIGO Laser Interferometer Gravitational Wave Observatory. These ripples in spacetime are produced when massive black holes merge. The detection of gravitational waves provides direct evidence of black hole interactions, offering insight into their masses, orbital dynamics, and frequency of mergers across the cosmos. Through gravitational wave astronomy, humanity has entered an era in which black holes are no longer purely theoretical. They are measurable, observable phenomena shaping the universe. Humanity has also simulated black holes using advanced computer models. These simulations allow researchers to recreate the extreme physics of singularities, accretion disks, and relativistic jets. By inputting data from observations and solving complex equations from general relativity and quantum mechanics, scientists can predict black hole behavior, test theories, and explore scenarios impossible to witness directly. Simulations help visualize how black holes interact with stars, galaxies, and surrounding matter, making abstract concepts tangible. Space missions have indirectly enhanced our understanding of black holes. Observatories like the Event Horizon Telescope (EHT) captured the first direct image of a black hole's shadow in the galaxy M87. This monumental achievement provided humanity with the first visual evidence of an event horizon, confirming decades of theoretical predictions. The EHT's success demonstrates the intersection of global collaboration, cutting-edge technology, and theoretical physics, highlighting humanity's ability to probe even the universe's most extreme regions. Black holes also serve as natural laboratories for fundamental physics. Near singularities, gravity is so extreme that it challenges the limits of general relativity, offering opportunities to explore the interface with quantum mechanics. Understanding these interactions may one day reveal a unified theory of physics. Humanity's study of black holes is thus not merely about cataloging cosmic objects. It is a quest to uncover the universe's deepest laws. On a broader scale, black holes influence cosmic evolution, shaping galaxies and stellar populations. Supermassive black holes regulate star formation in their host galaxies through feedback mechanisms, such as relativistic jets and radiation pressure. By controlling how matter moves and collapses, black holes influence galactic structure, star life cycles, and the distribution of elements, affecting the conditions for life in the universe. In this sense, black holes play a silent but critical role in the cosmic story in which humanity exists, even in theoretical contexts. Humans speculate about interstellar travel and black hole interactions. Wormhole hypotheses, while speculative, consider black holes as potential bridges to distant regions of spacetime or even other universes. Although currently beyond technological reach, these concepts inspire futuristic ideas for exploration, travel, and the expansion of human understanding. Black holes, in essence, expand both the physical and imaginative frontiers of humanity. Philosophically, observing black holes connects humanity to the cosmos in profound ways. The very act of measurement from X-rays to gravitational waves demonstrates our capacity to interact with phenomena billions of light-years away. This engagement highlights the scale of human curiosity and ingenuity, revealing that even the universe's most extreme objects can be studied, understood, and incorporated into our broader understanding of reality. In conclusion, humanity's interaction with black holes is a dynamic blend of observation, simulation, and imagination. Through advanced telescopes, gravitational wave detectors, computer models, and collaborative global projects, humans have brought black holes from the realm of theory into measurable reality. They not only shape galaxies, but also serve as cosmic laboratories, testing the limits of physics and inspiring new questions about space, time, and existence. Beyond observation and measurement, black holes have left an indelible mark on human culture, philosophy, and imagination. They challenge us not only scientifically, but also conceptually, representing ultimate extremes of the universe, places where density, gravity, and time converge into a singularity that defies ordinary understanding. Humanity's fascination with black holes transcends pure physics, touching art, literature, psychology, and the imagination. In literature and storytelling, black holes often symbolize the unknown, the inescapable, and the transformative. They are metaphors for danger, mystery, or existential reflection. In works like Interstellar or countless science fiction novels, black holes serve as plot devices and thought experiments, illustrating the consequences of time dilation, gravitational extremes, or hypothetical inter-universal travel. Through fiction, humans grapple with the philosophical implications of cosmic phenomena, making the abstract emotionally tangible. Philosophically, black holes prompt profound reflection on human limits, perception, and mortality. Approaching a black hole, an object experiences time dilation to an outside observer. It slows and nearly freezes at the event horizon. For the object itself, time continues normally. This divergence challenges intuitive understanding of time, illustrating that reality can differ dramatically depending on perspective. Black holes reveal that the universe operates under principles far stranger than human experience allows. Inviting humility and awe, black holes also influence art and visualization. The first images of a black hole's shadow, the swirling patterns of accretion disks, and simulations of relativistic jets have inspired artists, designers, and digital creators. These visualizations transform abstract physics into aesthetic experiences, enabling humans to perceive and emotionally engage with phenomena otherwise inaccessible to the senses. Art and science merge, allowing imagination to explore the beauty and terror of cosmic extremes. The study of black holes has expanded philosophical inquiries into the nature of reality. Consider the information paradox. If information entering a black hole is lost, what does this imply about determinism, causality, and the preservation of physical laws? If information is somehow preserved in subtle correlations, what does that reveal about the structure of space-time? These questions encourage humans to think critically about reality itself, exploring limits of knowledge, causality, and existence. Black holes are not merely objects. They are mirrors reflecting the boundaries of human comprehension. In addition, black holes inspire contemplation about the future of humanity and cosmic exploration. Could advanced civilizations one day harness energy from rotating black holes or explore near-event horizon regions? Concepts like the Penrose process suggest that black holes could, in theory, provide vast energy resources. Even if practically unreachable today, such possibilities spark imagination, scientific inquiry, and long-term thinking about humanity's place in the cosmos. Black holes thus encourage us to imagine futures far beyond Earth and conventional physics. Black holes also remind humanity of the interconnectedness of the universe. Each star, planet, and particle exists within the gravitational landscape sculpted in part by black holes. Galactic dynamics, matter distribution, and cosmic evolution all interact with these singularities. Recognizing this interdependence fosters a deeper appreciation for the complexity of the cosmos and humanity's small but conscious role within it. Black holes become symbols of universal order, chaos, and balance, revealing that even extreme phenomena are integrated into the cosmic web. On a personal level, contemplating black holes evokes awe and introspection. They are simultaneously terrifying and beautiful, representing ultimate destruction, yet also guiding cosmic structure. Humans experience a mix of fear, curiosity, and inspiration when confronting black holes, emotions that motivate exploration, scientific innovation, and philosophical reflection. This emotional engagement demonstrates the profound psychological impact of cosmic extremes on the human mind. In conclusion, humanity's relationship with black holes encompasses science, culture, philosophy, and imagination. They are objects of study, sources of technological and observational advancement, symbols of the unknown, and catalysts for philosophical reflection. By engaging with black holes, humans confront extremes of nature, explore the limits of understanding, and expand the horizons of thought and creativity. They remind us that the universe is vast, complex, and stranger than we imagine, and that the human spirit, through curiosity and imagination, can reach even the most distant and extreme corners of existence. Ultimately, black holes are more than celestial phenomena. They are mirrors of human curiosity, intelligence, and imagination, reflecting both our limitations and our capacity for wonder. They challenge, inspire, and guide humanity, bridging the gap between observation and imagination, science and philosophy, reality and possibility. In exploring black holes, we explore the depths of the universe and the depths of ourselves. Infinity is one of the most profound and elusive concepts in philosophy and science. It challenges the human mind, which is accustomed to measuring, counting, and understanding limits. Black holes, with their singularities and event horizons, serve as natural symbols of infinity, embodying extremes of density, gravity, and time. To contemplate a black hole is, in many ways, to confront infinity itself, force that defies comprehension yet shapes the cosmos. Humanity has wrestled with the idea of infinity for centuries. Ancient philosophers debated the infinite universe, the boundless nature of time, and the eternal recurrence of matter. Zeno's paradoxes, for example, explored the infinite divisibility of space and motion, questioning how finite beings could navigate an infinite continuum. Black holes, in a modern context, offer a physical manifestation of these philosophical puzzles, points in space-time where densities reach extremes. Time dilates infinitely, and our conventional understanding of physics breaks down. Singularities. The cores of black holes are perhaps the most tangible representations of infinity in the cosmos. In these regions, density becomes so immense that space-time curves infinitely, and the laws of physics as we know them no longer apply. For humans, this confrontation is both fascinating and humbling. It reminds us that there are realms of existence beyond our sensory perception, beyond our equations, and beyond our direct experience. Black holes exemplify the limits of human understanding while inspiring the pursuit of knowledge beyond those limits. The concept of infinity also raises questions about human perspective and scale. Our daily experience is measured in seconds, meters, and human lifespans. In contrast, black holes operate over millions or billions of years, affecting matter across thousands of light-years. Their singularities represent time and space, stretched to extremes that dwarf human comprehension. In studying black holes, we stretch our own cognitive boundaries, attempting to grasp processes that unfold far beyond the scale of everyday life. Moreover, confronting infinity invites reflection on mortality and existence. Just as black holes endure for billions of years, human life is fleeting, tiny in comparison to cosmic time. Observing the immense, slow-moving transformations around black holes can provoke existential introspection. Our lives are transient, yet we are capable of perceiving and understanding phenomena that transcend our temporal limits. This dual awareness of our fragility and of our cognitive reaches at the heart of humanity's philosophical engagement with black holes. Infinity in black holes also challenges notions of cause and effect. Near an event horizon, time dilates, and the flow of events differs dramatically between observers. What seems instantaneous to a falling object may take billions of years to unfold for a distant observer. This disjunction forces a reconsideration of linear causality, introducing a philosophical perspective where time is relative, experience is subjective, and the universe is more complex than intuitive understanding allows. In addition, the infinite densities of black hole cores provoke questions about matter, energy, and transformation. Does matter truly vanish at the singularity, or is it transformed in ways that we cannot currently perceive? Concepts such as Hawking radiation suggest that black holes release energy over time, returning matter to the cosmos in altered forms. Infinity, in this sense, is not simply an endpoint, but a transformational state of process in which extremes of gravity, time and space interact in ways that are both destructive and creative. Philosophically, infinity is also linked to curiosity and the pursuit of knowledge. Humanity's fascination with black holes reflects an innate desire to explore extremes, to confront the unknown, and to extend understanding beyond familiar limits. Just as sailors once ventured into uncharted oceans or astronomers mapped the stars, scientists now probe the extreme conditions around black holes, seeking to illuminate regions of the universe where infinity dominates. This pursuit embodies the human spirit, the drive to engage with what is vast, mysterious, and beyond comprehension. Furthermore, infinity challenges ethics and human responsibility in a metaphorical sense. Considering the scale and power of black holes, humans recognize their smallness in the cosmic scheme, fostering humility. This awareness encourages a philosophical reflection on our stewardship of knowledge, resources, and the environment. While we may never approach a black hole physically, understanding their power and scale shapes our perception of responsibility, perspective, and the consequences of action within a vast, interconnected universe. Finally, contemplating infinity through black holes merges science, philosophy, and imagination. These cosmic objects are physical, measurable phenomena, yet they evoke abstract thought about existence, time, and scale. In studying them, humans simultaneously practice empirical observation and philosophical inquiry, bridging the tangible and the conceptual. Infinity becomes both a scientific frontier and a mental horizon, a destination that inspires wonder, exploration, and introspection. In conclusion, the concept of infinity in the context of black holes challenges humanity to expand perspective, embrace humility, and engage in profound philosophical reflection. Singularities, time dilation, and extreme densities confront our understanding of space, time, and matter. In grappling with infinity, humans confront both the limits of the cosmos and the limits of cognition, transforming curiosity into a bridge between empirical science and philosophical insight. Black holes and the concept of infinity resonate deeply within human culture and emotion. They provoke awe, fear, and curiosity, shaping not only scientific inquiry, but also artistic expression, literature, and philosophy. Humanity's engagement with the infinite is as much emotional and cultural as it is scientific. Black holes become mirrors reflecting our relationship with the vast, the mysterious, and the unknowable. One of the most immediate human responses to infinity is awe. Witnessing or contemplating phenomena that dwarf our scale, the immense gravity of a black hole, the billions of years of cosmic evolution, the stretching of space-time elicits a profound emotional reaction. Awe combines wonder with humility, reminding humans of their relative smallness in the cosmos. Yet awe is not merely passive. It motivates exploration and creativity. It is this emotional response that drives scientists to build advanced observatories, to develop complex models, and push the boundaries of understanding. Fear is another powerful response. Black holes are often associated with ultimate destruction, stars being torn apart, matter vanishing beyond the event horizon, and time itself becoming distorted. Culturally, this fear has been woven into storytelling, art, and myth. In literature and film, black holes symbolize existential peril, the unknown, or the forces beyond human control. By engaging with these narratives, humans explore both cosmic realities and their own anxieties about mortality, the limits of knowledge, and the unpredictability of the universe. Curiosity, however, often surpasses fear, inspiring cultural and scientific innovation. Humanity seeks to understand black holes, map their influence, and even speculate about their potential as cosmic gateways. This curiosity manifests in art, music, and literature, where black holes become symbols of mystery, transformation, and exploration. They challenge creators to represent the unrepresentable, to translate extreme physics into forms that evoke emotion and comprehension. The swirling accretion disks warp light near event horizons, and gravitational lensing inspire visual artists and filmmakers to depict infinity in visually compelling ways. Black holes also influence philosophical reflection. In contemplating singularities, humans confront fundamental questions. What is reality when time and space behave so differently? How do we define existence when matter can seemingly disappear into an event horizon? These questions permeate human thought, prompting discussions in philosophy, metaphysics, and theology. Black holes exemplify the tension between what can be known and what remains beyond comprehension, a tension that has fascinated thinkers for centuries. In human culture, black holes are metaphors for transformation and rebirth. The destruction of matter entering a black hole contrasts with the eventual release of energy via Hawking radiation, suggesting cycles of death and renewal on a cosmic scale. This duality resonates with human experiences: loss, change, and the hope of regeneration. In this way, black holes inspire narratives that explore human resilience, adaptation, and the continuity of existence despite extremes. Emotions tied to infinity also influence educational and scientific outreach. By presenting black holes as gateways to extreme physics and cosmic understanding, educators capture the imagination of students and the public. The drama of singularities, the visuals of warped spacetime, and the science of gravitational waves make abstract physics emotionally accessible. Emotional engagement enhances learning, transforming the study of infinity from abstract theory into a compelling, human-centered experience. Black holes inspire cross-disciplinary cultural exploration. Writers, musicians, and visual artists explore their themes, integrating science with human narrative. Music, for instance, can emulate the tension, rhythm, and distortion of space-time phenomena, while literature explores psychological and existential dimensions of encountering the infinite. These creative expressions allow humans to interact with cosmic extremes emotionally, even if physical proximity is impossible. Finally, black holes foster existential reflection. Contemplating infinity encourages humans to ponder mortality, purpose, and the nature of knowledge. It reminds us that while we are finite, we can comprehend aspects of the infinite. This tension between human limitation and cognitive reach defines much of the emotional and cultural resonance of black holes. They are simultaneously terrifying and inspiring, destructive yet formative, alien yet intimately connected to human imagination and inquiry. In conclusion, black holes evoke a spectrum of human responses: emotional, cultural, and philosophical. Awe, fear, curiosity, and reflection intertwine as humans engage with phenomena that challenge perception and understanding. Through art, literature, music, and philosophical contemplation, black holes become more than scientific objects. They are cultural and emotional symbols of infinity, mystery, and human exploration. They allow humanity to confront the ultimate extremes, not only of the universe, but also of thought, imagination, and emotion. Confronting infinity through the lens of black holes is not only an intellectual exercise. It is a transformative journey that reshapes human perspective, philosophy, and future exploration. By grappling with these extremes, humanity gains insight into the limits of knowledge, the vastness of the cosmos, and the potential pathways for future discovery. This final segment explores how these insights can be integrated into science, culture, and philosophical understanding. One of the most profound lessons from infinity is humility. Black holes remind humans of their smallness in both time and space. Singularities and event horizons dwarf human lifespans, civilizations, and even entire planets. Yet paradoxically, this awareness of smallness fosters a deeper sense of significance. Humans are capable of observing, theorizing, and even measuring phenomena billions of light-years away. Infinity, in this sense, simultaneously humbles and empowers. It teaches that while humans may be physically minute, cognitive and imaginative capacities allow us to engage with the cosmos in profound ways. Infinity also underscores the interconnectedness of all things. Black holes influence galaxy formation, stellar evolution, and the distribution of matter across the universe. Recognizing these connections extends beyond astrophysics, offering a philosophical lens on causality, responsibility, and perspective. By understanding the forces that shape the cosmos, humans gain insight into the delicate balance of nature, the consequences of actions, and the intricate interdependence of existence at every scale. From a philosophical standpoint, black holes encourage humans to embrace paradox and uncertainty. Singularities embody extremes that defy conventional logic, densities that become infinite, time that stretches or halts, and matter that transforms in ways beyond comprehension. Confronting these realities nurtures flexibility in thought, openness to new ideas, and acceptance of the unknown. Humanity learns to navigate uncertainty not as a threat, but as a horizon of potential, a space where curiosity and imagination can flourish. Looking forward, infinity inspires futuristic and exploratory thinking. Concepts such as wormholes, energy extraction from rotating black holes, and interstellar navigation challenge current technological limits but inspire research, innovation, and vision. Even speculative ideas shape scientific agendas, motivating physicists, engineers, and space agencies to explore what once seemed impossible. Infinity thus becomes a catalyst for progress, bridging imagination and empirical inquiry. Black holes also offer ethical and existential reflections. By contemplating forces so vast and powerful, humans reconsider their place in the universe and their responsibilities within it. The awareness that the cosmos operates according to laws beyond human control invites a sense of stewardship, not over cosmic events, which are beyond influence, but over knowledge, technology, and the ways we impact our own planet and society. Infinity fosters both humility and ethical reflection, urging consideration of consequences across scales. Culturally, the confrontation with infinity enhances creativity and expression. Black holes and singularities inspire art, music, literature, and digital visualization. These creative works translate abstract, incomprehensible phenomena into forms that engage emotion, imagination, and intellect. In doing so, they connect humanity to the cosmos, providing experiential insight into concepts that exceed direct perception. Infinity, therefore, becomes both subject and medium, merging science with culture in ways that enrich understanding. On a personal level, engaging with infinity through black holes encourages self-reflection and philosophical growth. The awareness of cosmic extremes prompts contemplation of life, mortality, purpose, and curiosity. It invites introspection about the scope of human knowledge and the courage to confront the unknown. Infinity is not merely an abstract concept, it is a mirror reflecting human thought, aspiration, and the pursuit of meaning. Ultimately, integrating the lessons of infinity requires synthesis of science, philosophy, and imagination. Observational data, theoretical modeling, and philosophical reflection converge to create a multidimensional understanding of black holes and their cosmic role. Humanity learns to navigate extremes intellectually, emotionally, and imaginatively, transforming encounters with the infinite from abstract fear into tools for insight, creativity, and exploration. In conclusion, the philosophical journey of confronting infinity through black holes enriches humanity on multiple levels. It cultivates humility, encourages philosophical reflection, stimulates creativity, and inspires future exploration. Infinity is both a limit and a horizon, a force that challenges understanding while motivating engagement, imagination, and discovery. By embracing infinity, humans deepen comprehension of the cosmos, gain perspective on existence, and cultivate a broader sense of connection to the universe. As we approach the end of this extraordinary journey through black holes, the cosmos, and the infinite, it is essential to pause and reflect. Over the past chapters, we have traversed the formation of stars, the intricate anatomy of black holes, the possibility of traveling through space-time extremes, and the philosophical reflections inspired by confronting infinity. Each concept has challenged our understanding, stretched our imagination, and invited us to consider the universe in ways previously unimagined. This journey has not only been scientific, but also profoundly human. Black holes, as ultimate extremes of nature, have allowed us to explore the intersection of observation, theory, and imagination. They have prompted reflections on time, existence, and the limits of human understanding. They remind us that the universe operates on scales and principles that surpass our everyday perception. Yet we possess the curiosity, creativity, and intellect to engage with these cosmic phenomena. Throughout this exploration, we have seen that black holes are not mere objects, they are gateways to thought. They are mirrors reflecting human curiosity, philosophical inquiry, and the boundless imagination that drives scientific discovery. From their formation to their potential to influence entire galaxies, black holes embody both the power and mystery of the cosmos. This reflection invites us to appreciate the vastness of the universe while acknowledging the unique capacity of humans to observe, question, and imagine. As we conclude, it is important to acknowledge the human spirit that underpins this exploration. Science is a collective endeavor built on the curiosity, dedication, and ingenuity of countless individuals across generations. From early astronomers mapping the stars to contemporary physicists detecting gravitational waves, humanity's engagement with black holes reflects a shared quest for understanding, a desire to pierce the veil of mystery and confront the unknown. This moment is also one of gratitude. Gratitude for the natural laws that allow us to explore, for the instruments that extend our senses into the cosmos, and for the imagination that enables us to conceptualize extremes far beyond direct experience. Gratitude for curiosity itself, the force that drives us to wonder, to ask questions, and to seek answers even when the universe seems infinite and incomprehensible. Engaging with black holes also fosters a profound sense of connection. While we may be tiny in the cosmic scale, the act of observing, studying, and imagining links us to the universe in meaningful ways. Every photon captured, every simulation created, every gravitational wave detected is a thread connecting humanity to the cosmos. This connection reminds us that knowledge is not only personal, it is shared, extending across time and space, linking scientists, thinkers, and dreamers across generations and cultures. As we close this exploration, let us carry forward the lessons learned from the cosmos. Black holes teach us humility, inspiring both awe and curiosity. They challenge our perception of time, space, and matter. They invite philosophical reflection and ignite imagination. By contemplating these extremes, we deepen not only our understanding of the universe, but also of ourselves. The journey does not end here. Black holes will continue to intrigue, scientists will continue to explore, and humanity's imagination will continue to soar. The universe, vast and mysterious, invites us to keep asking questions, pushing boundaries, and embracing the unknown. Let this exploration serve as a reminder that while the cosmos may be infinite, our capacity to wonder, imagine, and learn is equally boundless. Thank you for joining this incredible journey into the heart of black holes, the edges of space, and the philosophical contemplation of infinity. May the curiosity, awe, and inspiration sparked here continue to guide your exploration of the universe, both outward into the cosmos and inward into the infinite possibilities of the mind and spirit. As we reach the end of this journey through black holes, infinity, and the mysteries of the cosmos, it is time to pause and let the vastness of what we have explored settle within the mind. From the formation of stars to the enigmatic singularities, from the bending of time near event horizons to the philosophical reflection on infinity, we have traversed realms that challenge comprehension and spark awe. This journey was not merely a series of facts or scientific concepts, it was an invitation to explore, imagine, and reflect. Black holes, with their extraordinary power and mystery, have served as both subjects of study and symbols of human curiosity. They remind us that the universe is far greater than our daily experience. Yet we possess the capacity to understand, to wonder, and to dream beyond our limits. As you listen, perhaps lying down and preparing for rest, Allow the scale of the cosmos to inspire a sense of calm and humility. Let the images of swirling accretion disks, warped light, and infinite singularities expand your imagination. Consider the courage of human inquiry that has brought us even this far into understanding these cosmic marvels. And let this awareness nurture both wonder and serenity. Finally, let this moment be a tribute to curiosity, imagination, and the pursuit of knowledge. Thank you for joining this journey through the universe's most mysterious phenomena. May the awe and inspiration sparked by black holes guide you in contemplating both the cosmos and your own inner universe. As this video comes to a close, breathe deeply, relax, and let the universe's infinite possibilities settle around you. Sleep, dream, and carry the wonder of the cosmos into your own consciousness, knowing that the mysteries of the universe are always waiting, infinite and inviting, for the next journey.